La la. Okay, so hopefully we is live. Do you get notifications when I go live?
Who, me?
Yeah,
Probably not.
you. Oh,
Probably not
so
now.
you don't have my YouTube?
I don't know.
Well, if you don't get notified, then probably not.
When I type in Mr. Slave, your channel doesn't come up. Other people's channels come up.
Yeah,
PWF Clips comes up, and
yeah,
all these all these
yeah,
other people come up.
yeah. I
Playing with
know.
Fire, The Crucible, all these other guys.
Yeah, I'm up to 196 subscribers. Can you believe it?
Can't believe it.
Oh, so many. But each one is like pulling teeth. It's very difficult to add the subscribers. Anyway, let me share my whiteboard with you. You can watch my stream. It would be easier for you to watch the stream. I'll give you a link to my stream. I'll put it in the side chat. Side chat. Side chat. Here's the link. So why don't you go ahead and click. Oh, do you know what is clicky no linky? Can you guess what is clicky no linky?
Is it like subscribe to my YouTube channel? That
Well,
it?
but specifically, what is clicky no linky? What is clicky no
Is it
linky?
download the AI clickless cage? Is that
No,
it?
no.
Is it?
So in Portuguese, no means you reverse the letters. It's on. So click, and every word ends with an e. It's like they can't add a word like without e. They have to extend it. So clicky is click. No
Mm-hmm.
is on. Linky is just link. So clicky no
Ah,
linky is just click on the link.
I see. I see. Yeah, it says you have 196 subscribers.
Yeah, yeah.
You know what I love? You know that guy with the Jack's Films or something like that? He had a video where he was celebrating 1 million subscribers, and when he did it, like everyone was watching him, and like to fuck with him, they all unsubscribed. So he never reached 1 million. He got like the 99,900 and something, and they all unsubscribed, and it kept going down.
Wait, why did they do it?
Just as a prank to like mess with
Oh, Mr. President of Earth has joined the chat. Mr. President of Earth.
Hello.
El
Mr.
Presidente.
Mr. President of Earth, I found a contradiction between my ether model and Einstein.
Is that a contradiction or just a
Okay.
disagreement, though?
It's actually a disagreement because I don't know if Einstein has been proven to be correct about it. So we'll see. Anyway, the contradiction is as follows. So you President, you can watch it on the YouTube stream. It's on the side. The link to the YouTube stream is on the side chat if you want.
Okay. I'm eating right now. I will
You're meeting
respond in
right
a
now?
bit.
Oh, you
I'm
You're
eating, eating.
oh
or
you eat,
eating?
so you cannot watch your like YouTube.
Okay, 1 second.
Hmm. Tell me when you're ready, and I will present the contradiction. La 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 la. Which is really weird because everything else fits, but this thing.
What's the contradiction?
So the contradiction is as follows. So we have the S frame of reference. This is one rubber ducky. We call him S, and this is the other rubber ducky. It's called the S prime rubber ducky. The S prime rubber ducky is moving at velocity v to the right. So this is the S prime rubber ducky at time t equals 1, at time t equals 2, at time t equals 3. So the S prime Oh, Da Vinci left. So the S prime rubber ducky, its clock is ticking slow because it's moving through the water. Okay, right? Do you see how the
Yes, yes.
it's time dilated? Okay. Now every time S prime's clock, every time S prime's clock ticks, it sends out a message. It sends out a signal that is picked up by the special detector on the S frame of reference, the S ducky. So the
Yes,
S,
yes. I know this experiment.
what do you mean? I never described it. I created it last night.
It's how I don't know the name, but it's the first logic. How can I say it? That proves the time dilation with reference frames.
Right, but these are rubber duckies in the bathtub. So so S prime, we can see it is being time dilated. Its clock is time dilated because oh shoot, it reset every time it resets. Okay, so S prime is time dilated. We see the clock time dilated. Okay, so its clock is ticking slow, whereas the S frame of reference duck, its clock is ticking normally because it's not moving relative to the ether. Okay, now wait, somebody texted me something. Yes. Yes, very good. Very good. This is the time dilation part. That's fine. But I'm adding something to the discussion. I mean, I don't want to, like, I'm starting from first principles in a bathtub. This is a rubber ducky experiment in the bathtub. So, yeah, you get time dilation. Mhm.
Where do you start, basically? How do you explain that
What?
the Einstein's thought with the image I sent is because they had measured that the speed of light is constant. You can then derive this without any assumptions. This comes from constant speed of light.
Right,
There is no need for assumptions.
right.
It's and this is why it's real.
Okay, but I'm not talking about Einstein right now. I'm starting from first principles. I'm starting from a bathtub, and I want to show the contradiction to Einstein, which is really weird because I don't see why there should be a
Okay,
contradiction.
okay.
So, so we see from first principles that the rubber ducky's clock is time dilated. We see that here in this diagram. That the right instead of going up and down like S. Oh my God! It's resetting every time I touch it. Jesus, so many bugs.
You
Discord.
can you can say the conclusion to me, and I will understand.
Okay. So every time the clock in S prime ticks, it sends a signal out and it gets picked up by S. So S sees the signal. And we're ignoring the angle. There is no angle. So we have to assume that the distances are very far. So there's no Doppler shift. So everything is basically S is looking at S prime. S prime is really far. So there's no Doppler shift to worry about. Okay. So when S is listening, this is the S external clock detector. It's listening to the S prime clock ticking. So if we compare S's internal clock to S's external clock, which would be ticking faster and why? What do you think?
Can you repeat that last part?
Hmm, of course. So
And also, I have something to say about the really far part.
sure. So
How much is really far?
infinite. Like on the other side.
then you cannot do any calculations. It's like
Why not?
it's not realistic. It's just for understanding some principles. This example, the real far distance, which is infinite.
Wait, if I'm looking at a galaxy on the other side of the universe and it's
It
completely.
has a distance. It still has. If you can you scroll so I can uh, explain better?
Yeah,
Can you scroll the to
yeah, yeah,
the down
yeah.
part?
Okay. Yeah.
Yeah.
Can you see it? Yeah.
So S like how is it called?
S prime.
S prime is the
Moving.
bottom or the okay. So S prime
Hmm.
still has will always if we are talking about real uh, uh, like a real situation,
Okay.
which we have to talk about the real situation,
Okay.
it will still have an angle towards you. It will still be at an angle because it has speed, and even if it's 10 billion light years away, it will still have a minuscule angle that will change. So the time dilation exists.
Okay. Let's make it a very big pool. Let's go back to a pool. So let's forget about light. So in a pool or in a bathtub, a very big bathtub, let's say 10 meters by 10 meters. So on one side of the pool, so let's say they're 10 meters apart. So this rubber ducky, it's very tiny, and S prime rubber ducky is very tiny, and they're 10 meters apart. So there's basically no angle. The theta here is negligible, right?
It's negligible, but it exists.
Yeah,
It's
it exists, but it's negligible.
yeah.
I mean, for our scenario. Okay.
Okay, okay. I'm overthinking stuff, and
Okay.
your conclusion is something else.
Yeah, well,
Okay,
we can
yes.
always come back if you want to change your mind. Anyway, so I'm just saying this angle is basically zero. So the question is this clock is ticking, the internal S clock is ticking, and the external S clock is ticking. The external one is
Yes.
ticking because it listens to the S prime clock ticking. So the question is which clock is ticking faster? The
The S prime because it moves. Oh, faster. You mean
the
if it moves, since S prime moves, it experiences time slower. It experiences time dilation.
so let me just make it a different color.
You can do the calculation. It doesn't matter if it's negligible because it's far away. It still has a number, and you have to plug this number in the proven equations, and you will find out.
So, which one in the S frame of reference, which clock ticks faster, the green or the red?
The green or the red? Wait,
Hmm.
is the green one the upper, the moving? Uh,
The green one, yeah, it listens to the S prime, but the angle is zero. I just want to make sure you understand this angle is zero. It's
wait,
far,
wait, wait.
they're
How?
actually,
It's not even you can do the calculation. It's two equations.
no, no,
You will
forget
see
about,
that there is
look, it's a bathtub. I don't care about numbers. I just
yeah,
want to
but
know,
you start from the conclusion of Einstein that
no,
there
no,
is time dilation,
no, no,
and you
this
go
is,
backwards.
no, no, this is a bathtub. These are rubber duckies in a bathtub. Forget about
Yes, but they have clocks, and you have clocks, and you compare them. This
yeah,
is time dilation.
yeah, but we don't need. I don't want to talk about Einstein. I don't
Wait,
want.
it's a different universe, right? Let's
No,
assume it's a
no.
different.
This is my. This is a bathtub. It's just a big bathtub. The distance between them is 10 meters. Each one.
Okay,
Each one is 10 centimeters big. The distance is
yeah,
10 meters. This is not the
okay,
scale. So this is, let's say, 10 centimeters, but this is 10 meters.
okay. It's a super realistic scenario, right? No assumptions or.
Correct. Correct.
So, what's the speed, let's say, of the moving rubber ducky?
Let's say 1 meter per second.
Okay. And what's the question again?
Which S clock is ticking faster, the red or the green?
The stationary one.
The internal one is ticking faster. The red one is ticking faster.
What do you mean as internal?
The yellow.
Oh, internal. Okay, okay. Yes, yes. The moving rubber ducky's internal clock is, let's say, ticking faster. It goes faster into the future
but
because it moves.
but the
It has a
moving
speed.
but the moving no, but look, because it's moving, there is a bigger distance that the wave has to travel before it is
Yeah.
detected. So is it
Ah, okay. I understand your confusion. I thought I got what you are. So even if it's a bigger distance, this means that in the reference frame of the moving rubber ducky, since the speed of light is constant, it experiences that the other things outside it, the non-moving things, are
no, I'm just
like
look, we are God. This is a bathtub. We're
yeah,
we're looking from the top at a bathtub.
yeah, yeah, yeah.
So
I understand.
we can see the green ticking and the
Look, you have to understand reference frames and how they work. It's a
no,
bit tricky.
no, it's a bathtub. This is just a bathtub. This is just a
So we throw, just for this experiment, we throw all real relativistic effects out the window, right?
this
And
is a
we
bathtub. This is a baby. We are babies in a
wait.
bath.
The waves. How do you measure the wave speed in water waves? In the for the clock, the are the red things waves?
We're looking. Yeah, these are waves. We are
Water waves, right?
yes, water surface
Okay,
waves. Yeah, we
okay,
are normal people playing
yeah,
in a bathtub with rubber duckies. Each rubber ducky has a clock that is ticking in the waves, and as the right, you see D and D prime. So as the rubber
yeah,
ducky moves at velocity 1 meters per second, instead of D that the wave needs to travel before it is green detected, now it has to travel D prime before it is red detected. So you see the time, you see this clock will tick slower
yeah,
because of the
yeah, right.
velocity. All right.
Yes.
So
But look, I
yeah,
know, I know, I know. I understand what I'm going to answer. I understand the whole thing. You have to understand that. Let's say in this situation, let's say that the water wave speed is the maximum limit, right? This is the only way that we
no,
can.
no, it's just one. Oh, what is C? Okay, let's define C.
Yeah,
C is, let's say, 2 meters.
5.
Yeah.
Yeah, yeah,
Okay.
2,
Yeah, two.
something like that. Yeah,
Yeah.
because it's the maximum speed. it's the same thing as you will have the same thing as special relativity predictions, because you look, you have to understand. I will send you some.
No,
You have to search it for yourself, but you have to understand the reference frames and
no,
how
no, no.
uh,
Right now I'm just
different.
asking. No, no, no. I'm just asking a simple question. Which will tick
Yeah,
faster, the green or the red? That's all.
yeah. The moving one will
No,
experience
no,
time
no,
dilation.
no, no, no. Look, S is not moving. S prime is moving. So S is
Yeah.
not moving. S has two clocks, internal red, external green. Which will tick faster?
What do you mean
The internal
external? The way we
external
perceive it as outside
no,
of us.
no, no. Look at the waves. External listens to S prime. The green clock listens to
Okay.
S prime ticking.
Okay. Why are you comparing it like this?
Just what? What do you mean? Just answer the question. It's a right. It's theoretically it's a simple question. I mean, I think at this point it's a straightforward question. I mean, I think all the information is available, right?
I-
You have
Look,
Mhm.
the S prime, the moving
Yes,
one,
yes.
will. I'm not sure how to explain. It will see things outside it go
No,
faster.
no,
What's
no,
the
no,
thing in English?
no,
I'm
no,
not.
no. I don't. I
I cannot
I
explain it.
no. It doesn't have a brain. It doesn't see. It doesn't have eyes. It doesn't have a brain. It doesn't have.
It doesn't matter, but we see that if we let the clock inside it
But
will.
that's not the question. Listen,
Okay.
S prime is moving through the water, and
Yeah.
it has a clock that is ticking through the water. This is a tick. This is a tick.
Yeah.
This is a tick. You can see that
Okay. Yeah.
because
It's
D,
not the same position
yeah,
every
it's
time.
longer, so it's
Yeah.
slower. So
Okay.
this ticking is slower than this ticking, right? We're looking at the rubber ducky. We're
Yeah. Okay.
normal
Okay.
humans.
Yes. Yes. Yes.
Okay.
Yes.
So my question is, this red dot is every time the S clock is ticking. Tick. That's an internal clock.
Okay.
The green one is external. It doesn't have an internal mechanism. It just listens to
Yeah.
S prime ticking.
Oh. Okay. I understand now.
So
I
now
think I understand.
which is ticking faster, the red or the green?
The red.
Okay.
Oh, I understand. Yes. Look, it's. I think it's the red because it still has a longer. It has a yes. It has a longer area to travel.
Which?
The other signal. The external clock. How did you call it?
Yeah.
Yeah. Yeah.
So it's going to tick slower?
Yeah. Yeah. Yeah.
Why?
It has a long. The light, since it's
No, there's no light.
steady speed.
It's water.
You know the
Water.
water wave,
Yeah.
basically light in this situation. The same thing. Where it has it has a constant speed and it
Hmm.
has a longer area to
But
traverse.
what do you mean longer?
Longer,
What
more meters.
are you referring to, this distance? The distance between S prime and S?
Yes, because the S prime is traveling and
No, no,
will.
no. But this is far away. This is 10 meters away. You have to remember
Oh, okay, okay. Yes,
it's far away.
it's still the same. If it's not infinite distance, it will have still a minuscule amount more to travel.
Right, but S prime is ticking, it's ticking many times. It, it's like there's three incoming ticks. You see here. Oops. You you what? Okay. You see one tick, one wave, second wave, third wave. So S is hearing boom, 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 boom. It has incoming waves. It has
Yeah.
these incoming ticks,
Okay.
and simultaneously it has an internal clock. So they're
Okay.
ticking simultaneously. But which is
It's not
no,
simultaneously,
listen,
but
listen, let me finish the sentence. They're ticking
okay.
simultaneously, but which is ticking faster? Uh,
How they tick simultaneously since
They
it's
don't, they,
far? It's also a longer distance due not only due to the movement, but due to the
but it's like,
super long distance.
right, but there is waves that are already impacting, right? I can move this to here, and this to here, and this to here, and I'm asking, right, these three waves are about to impact S. When they impact, it's going to be boom, 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 some rate.
Oh no, no, no! It won't. You can do the calculations.
No, no.
I think you should. Yeah, yeah. I'm one
What do
hundred
you mean?
percent
What
sure.
what calculation of what? The rate is the distance. The rate is the time between ticks. I don't care about this distance. Now
Okay, okay. I understand.
these ticks are arriving now at S, and simultaneously S is clicking internally. So these clicks are arriving at S. Simultaneously, its internal clock is ticking. What is the rate of this ticking compared to this ticking? Which is faster? They're happening, basically, they're happening simultaneously, but at a different rate. Or is it the same rate?
Okay, I kind of understand. I understand far better now.
Okay.
It will be look. It will be still slower. Yes, because
Which?
it's also moving.
Which will be slower?
The coming waves will have a distortion. Let's say
No,
they
just
will be larger wavelength.
which is no. Which
Yeah,
is
that's the answer. You
no,
can
no, no, no. Which clock is ticking faster? I don't care about wavelength.
the internal one of S.
The internal is ticking faster?
Yeah.
Why?
You can I cannot explain it with
Why not?
words. I explained it. I said the S prime is moving. It experiences time dilation,
Okay,
and
good.
so it will. If we let's say, how can I explain it?
I mean, I'll tell you
I
how
cannot explain it very
you.
good,
It's okay. I
but
mean,
this is my answer.
yeah. So I agree. So in this scenario, that S prime is moving, it's time dilated, so it's ticking slower than this. That we see S prime ticking slower than S. We see it. And S is listening to the
Yeah,
slow ticks.
yeah, yeah,
So
yeah.
these
Right,
slow ticks will be slower than the normal ticks.
right. Yes, that's it.
You could even say, let's say that this is not one, this
You
is
can compare it to a movement of like you're someone that travel is traveling faster, like very fast. If he
exactly
moves his hand, you will see him do it slower than usual. That's the same thing, basically.
right. So you
Yeah,
can switch this to 1.999.
yeah.
When it's 1.999,
It's
basically
almost
it
stationary.
exactly. It's not, it's unable. This D prime becomes almost infinite, so it's
Yeah, yeah,
barely ticking.
yeah,
Right. Okay, that makes sense. Very simple, right? So
yeah.
you agree that this is identical. The equations are identical to Einstein's special relativity, right?
Yeah, it's how he came up with special relativity.
I don't think that's how he came up because I didn't assume the speed of water waves is a constant. I didn't assume that. I mean, I did, yeah.
It is. If you measure it, it doesn't matter. In our reference frame, it is constant if you measure it.
Okay, but I don't think this is it. Okay, whatever. This is Einstein SR compliant. This is
Yeah.
completely. That's good. Fantastic. Now let's switch around.
Okay.
Now S will be moving at V, and S prime is stationary.
Okay.
We're playing with the toys, so we decide who's moving, who's not.
Yeah.
And again, the same question. This is the internal S
Yeah.
clock, and this is the external S
Yes.
clock. Which will be ticking faster?
We are. Where are we sitting? Are we a
Ab-
stationary observer or
yeah,
inside the first
we
the
are
S box?
we are playing with rubber duckies in a bathtub. So we're looking from above. This is the top view of the.
Okay. 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 Still, the slower moving rubber ducky will experience time. Uh, look. You are measuring pulses from one moving thing to another moving thing. So you have to choose inertial frame. You cannot do that.
I'm looking at the rubber duckies from the top. This is a top view of toys. These are toys. I can reproduce this
Yeah.
in.
Okay. Still, so you are a stationary observer. Okay, that's
Yes, I'm
how
a station.
they call it.
Yes, I'm a
Yeah.
stationary observer looking at.
The clock of the S,
Yes.
the internal clock, will
Yes.
tick still faster than the
No.
thing that receives
No. S is
the
moving.
pulses.
S is
Yeah,
moving.
still.
What do you mean
Is it
still?
faster than the other? What speed do they
S
have?
prime is V0. Let's write it down. So this guy V
So
equals
S
zero.
prime doesn't move now, and the other one moves.
Yes, we reversed it. Yes.
It will happen the same thing as the above
How?
one.
What? But S,
You just made the previous one. It's the same thing,
but S clock
just
is,
in opposite.
wait, S clock, is it time dilated or not?
Is it moving?
Yes, S is
Yeah.
moving.
Oh, the S clock is receiving still. It's still receiving the
Yes,
pulses, right?
yes, yes.
Okay, okay. So it will receive a faster pulse. The external clock of the receiver of S will be faster than the internal clock.
Okay, so
Yeah.
S is moving, so it is time dilated, and you could say that if V is equal to 1.99999, so S is basically stopped.
Yeah.
S internal is stopped.
Relative to the external observer, us, for example.
Yes.
At this speed, each external clock will receive a very high frequency, like oscillation, let's say, from the other clock.
Let me just.
Look, I have to go. I will return later. I cannot.
Okay.
I have some things to do.
Just think about
Okay.
it. This
What's the final?
this
What are
is
you trying to
this is
conclude?
this is a violation of Einstein's special relativity. This proves Einstein must be wrong.
No, no. That's I'm using in my head the special relativity to solve
No,
this.
S is seeing
Yeah.
S prime ticking fast, but
Yeah, that's time dilation.
S cannot know that it's moving. S cannot know that it's moving, and it.
It does when it accelerates to reach that speed relative to the other. This is how things
But
work.
this is a bathtub. What do you mean it accelerates? Einstein's special relativity doesn't have
You are
acceleration.
look,
You
if you
didn't.
are talking for a purely hypothetical scenario without realism, you cannot do anything. It's not going to work.
No, given. Okay,
In reality, you have to accelerate the S
when are you coming back?
rubber duck.
When are you coming back?
About in a hour or so, I think.
Okay, I'll be here. Okay, come back. We'll
Okay, okay,
continue. All right, see you.
okay. Have to go. Okay,
Okay,
bye bye.
okay, bye. Okay, that was a very important discussion. So I think Einstein is wrong. I don't have any way to save Einstein this time. Now, everything else is mechanical. Einstein is not mechanical. Einstein is magical. So I can't save Einstein. And I don't think this experiment has ever been done. I think, sorry, Einstein. I can't save you this time. Can't save you this time. I'm so sorry. Okay. This, I waited since the beginning of my thought experiments. I saw the problem. From the beginning, I noticed this issue. And I said, I'll come back. I'll come back. I'll figure everything out. I'll come back. Everything, I think everything fits into place. Very advanced stuff, especially gravitational time dilation, gravitational lensing, black holes. Everything falls into place except for this simple thought experiment. This is bizarre. Let's see. This server, is there anyone? Oh, there's a few people. Omnivore. Oh, he's not listening. Let's see if there's somebody here who can talk. Oh, there's no one here. Oh, no one here. No one here. hmm Let's see these guys.
186 bars of pressure, I think it was, which is 16,000 psi.
Yeah, that's insane. And keep in mind, the best submarines, I think they go only up to a few thousand feet, right? How deep is this?
Yeah, I think it's not zero point 0.9 miles. I think is the lowest. The that is 6 miles deep.
Hey guys,
6 miles.
6 miles deep, and the capsule is made out of foam with like a hollow sphered something. It's some kind of material, but it's definitely foam.
Hey guys, does anybody want to talk about relativity?
Yeah.
We're on a different subject.
I want to, of course. You want to go?
No, I'm just playing. I know that's what you're gonna say, dude.
No, you're not gonna believe it. I found a contradiction in Einstein. I can prove it. Einstein is wrong.
Oh, we're on a topic.
You mean Einstein? Who's this Einstein guy?
Einstein. It's Einstein.
He was in Rammstein, and then he was like, they had to he's the drummer or something.
You
Yeah,
came here
Rammstein.
immediately dropped 2 Einsteins. Like you're approaching your limit already. That's crazy. You're limited to 30 now. You know.
Wait, you're only allowed to say Einstein 30 times a day?
That's 3 times now. Okay.
Oh,
You
okay.
have a limit.
Oh, okay. Anyway, does anybody want to see the proof Einstein is wrong?
You think they went? Do you think James Cameron made it to the bottom of the Marianas Trench in his submersible, or do you think he just faked it for the lulls?
Who, me?
He's a new fiction.
So does anybody want to see the proof?
Wait, I thought we were on the Marianas Trench thing. I was curious about that.
Yeah,
Well,
we're
he's just
talking.
gonna
We're
bump us
on a
around.
topic, dude.
No
Get with the
problem.
program, bro. Come on.
Look, I thought you guys want to prove Einstein wrong. Like, I thought you guys.
No,
No,
do you
we don't.
Do you
No, we
think
don't.
he made it to the bottom of the Marianas Trench,
Who, me?
Mr. Slave? No, Mr. Slave.
Yeah, I'm in general, I'm mainstream, but now I have proof that Einstein is wrong.
You're just gonna keep doing that, aren't you?
He's just gonna keep saying the same thing over and over. Okay, let's
Like,
just
is
ignore
it
him.
11 now? I'm not counting. Really.
So
Wait, I said
Elbow. What else?
No, I answered. I said in general, I believe.
So
yeah, and I believe.
so
yeah.
check out that picture I posted.
What about it?
That's supposed to be, yeah, that's supposed to be 6,000 or 35,000 feet down, 6 miles.
Where?
I
Oh,
like how they did the same thing with the moon landing. Like they had the camera hand.
Yeah, how did
Well, like,
they
banana
take
dick
that
comes
picture?
down.
oh, they muted
I don't
me.
understand.
It just like
Why
left
would
the
they
dude
mute
down
me?
there.
Wow, what
Mariana.
idiots.
Yeah, they.
Idiots. Absolute idiots. All right, so this server is empty. Let me see, in politics and religion, there's nowhere I can discuss this. There's no one I can talk to. It doesn't matter. You know what? It doesn't matter. Let's stay on topic. Let me see. Tests of general relativity serve to establish observational evidence for the theory of general relativity. The first three tests proposed by Einstein in 1915 concerned the anomalous precession of the perihelion of Mercury, the bending of light by gravitational fields. That's nothing. The gravitational redshift. That's nothing. That I can explain. I don't know the perihelion of Mercury. I don't know how that works. The precession of Mercury. Okay, I don't know about that. Special relativity is a physical theory. It's not. That plays what? Read it all, not descriptions. XD, don't cheat. Jesus Christ. Wait, I'm reading I'm reading. I mean, when you come back, we can discuss. I just told you, I don't have a problem with anything except for the precession of Mercury. I don't know what the proof is. I'll look into it. Like I don't know what tests did special relativity go through. What tests? Because I think Einstein is wrong on this issue. You know that until today, I try to be compliant with mainstream, but now I can't. I can't be compliant. I see a problem and I don't know what to do. So I'm making a prediction. Einstein is wrong. It should be easy to actually test it and see who's right, who's wrong. I think Einstein is wrong. But if he's right, then I have to figure out why he's right because mechanically he's wrong, and mechanically everything else fits. I am compliant with all the data that basically except for Mercury's perihelion, whatever. I don't know how that works. You know what? Let me look into Mercury's perihelion 1 second. Let's see what's that about. Mercury's when when is this happening? Notification. Okay. Why Tim Pool pisses me off? Yeah, Tim Pool has become basically Putin. Putin. He's not a Putin shill. He's just Putin. I mean, like Putin is not a Putin shill. Putin is Putin. I mean, Putin and Tim Pool believe in God. They believe in magic. All the same. Who measures what? Who's measuring proper time and that's exactly the question.
So what I have here today is I have a measuring tape. Today we're going to be talking about proper length and proper time. So what I have here today is I have a measuring tape that I put in my coordinate system on the ground, and I have a clock, which will also stay with me in my coordinate system. Now, meet my friend Bob. Bob here, he also has a clock, and he has a measuring device with him. As long as Bob is not moving relative to me, the time elapsed between two events that Bob is measuring.
This is the problem with all these thought experiments. Very nice, but I need to see an actual experiment. You cannot continue with these endless thought experiments. At one point you have to say, let's conduct an actual experiment. Show me an actual experiment. Stop with the nonsense. I can prove to you. I can do the same thought experiment, and I can prove to you you're wrong. So that's a dead end. Let's stop the nonsense. And people, you go to YouTube, and you have all these YouTubers, and they're all contradicting each other, and who knows who's right? Let's conduct an experiment. Let's stop wasting time with all the thought experiment. A thought experiment is wonderful, but at the end, you have to conduct an actual experiment. I mean, we're trying to figure out the universe, not our brains. I don't care about my brain. My brain is great as a tool to figure out the universe. It's not, I don't care about my brain. I don't care what my thought experiment says. It's nice. Everybody has their thought experiments. Everybody has yoga. Everyone has their thought experiments. That's very nice. I don't care. I don't. Einstein is nothing but a thought experiment. I can come up with other thought experiments. I don't care. According to this, like every thought experiment, you heard what he said. Oh, it's acceleration. What? Who's talking about acceleration? It's given. I'm starting from. Where's? Oh my god! I have to go back into the whiteboard. What a headache. 10,000 days later. I'm starting from a condition. This is what's given. No one is accelerating. It's given. S is moving, S prime is not. Which clock is ticking faster? I don't care about acceleration. This is after acceleration. Everybody, you didn't say anything about acceleration before. Why do I care about acceleration? You wake up one morning inside a capsule. You don't know if you ever accelerated. So just tell me what's going on. Tell me, make a prediction. Now, if you cannot make a prediction, you don't have a theory, right? A theory needs to be able to make a prediction. So you don't have a theory. You have garbage. Oh shit, I'm not sharing. You don't have a theory. If you can't make a prediction, if you have to say, oh, we're accelerating, not accelerating, I don't care which is moving faster, which clock is ticking faster, and why. Now, if you're gonna say acceleration, I'm gonna say I don't know the answer. I don't know. Right now I'm moving, and I see somebody moving. I don't know who accelerated, what acceleration. I don't know. I'm one guy is moving, right? Especially now we're talking about a bathtub. But this is a bathtub. So obviously, the bottom guy is going to see, right? S is going to see S prime ticking faster and faster and faster and faster and faster and faster. S is going to be observing S prime ticking at the speed of light. It's going to be super fast. That's 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 from this thought experiment. Nothing to do with acceleration. It has to do with water, with moving, with waves. And if you assume you want to call it ether, call it ether. You can call it the quantum foam. The quantum, right? The quantum foam is right. Unless you're going to tell me the quantum foam, right? It's inconsistent. I mean, if you believe in the quantum, that's why I ended up coming up with the ether with an absolute frame of reference because it didn't work. This magical thinking doesn't work. It ends up with continuous contradictions. If you have a problem that we never discovered the ether, fine. That's 150 years ago that we last tried to find the ether. How about we try today? 150 years ago? That's the best you got? Well, 150, not a year and a half ago, not 15 years ago, 150 years ago, 1870 is the last time, or that's Michelson's experiment. Everything is based on Michelson's experiment from 1870. It's 30 years, it's 54 years, 154 years ago. You dare tell me that I'm wrong. There is no ether because 154 years ago, you're basing it on one experiment 154 years ago. You're out of your mind. Everything falls apart, yet you're holding on to one experiment from 154 years ago. Is that science? That's all you got? All right. Well, that's nonsense to me. That's completely nonsensical. What is this? Uh, public room. Hello. Hello? Hello? Am I inside? Can anybody hear me? Hello? I don't see me. Let's try this again. I don't see me here. I'm not here. That's weird. It's voice locked. Hello? What's going on? I cannot see me. I can't hear anyone and I can't see anyone. You do not have permission to speak. Okay, and this guy? Alright, I don't know. Let's try that again. Join voice. Nothing. Hello? You can't text? What kind of server is this? What's going on? Okay. This is a waste of time. Okay. This is what democracy looks like. This is what democracy looks like. Okay, so what I think I need to do. So that was a useless server. Let's move it all the way to here. What about flat Earth? Is this a good server? No, it's an empty server. Mm-hmm. Mm-hmm. These guys are useless. This server hasn't woken up yet. They're probably like in California. Okay, I don't want to waste my time. Let's wait for people. What I do want to do is right. So getting back to this, this is physics. The 2024 Nobel Prize in Physics did not go to physics. This physicist is very surprised. Okay. Okay, what is this guy saying? I could not hear anyone nor see myself in the list nor talk. So I don't know. We'll try it again. Hello? No, I'm not. I'm not in the list. I think you have to wait a minute and they let you in. That's if you're interested. Where is it? Okay. Okay. I'm waiting. Okay. Back to this guy. So my notes are now written in terms of Bob. Okay. Another day, another boring thought experiment. How about showing us actual experiments? How about that? Has this been tested? Please show me the test. No more thought experiments, please. Thought experiments, thought experiments, thought experiments. Like, that's all you got. Thought experiments. Okay. All right. I heard, I heard enough thought experiments for a lifetime. Enough thought experiments. It's like everybody has to be compliant with Einstein. Why? Nobody knows. Nobody knows. This is like the emperor's new clothes. Everyone has to be compliant with Einstein. Why? Nobody knows. Casual? What's going on? Beyond the imaginary? Okay. Well, they're still not letting me in. Live chat. Waiting room. Oh, maybe this guy? You don't have to. Oh, you go here first. Live chat waiting room. Okay. Now I understand. So you wait for them to let you in. What kind of a server is this? It's like, this is the weirdest server in the world. You cannot welcome. Read this. Okay. Join voice. Okay. You cannot text. Oh, Omnivore is here. Oh, Omnivore has been invited. Contradiction to Einstein. Let me send him an invite. Let's see if he shows up. Hey, can you hear me?
I can, but I may have to jump real quick. Somebody else is pinging me, and I may have to go.
Yeah,
Go ahead, tell me.
I was waiting next to you. That's where I saw you. We were waiting for the same VC.
Yeah.
So,
Okay.
anyway, how do we know that Einstein is right in special relativity? What's the evidence?
For special relativity,
Yeah.
you mean like as opposed to general relativity?
Well, let's start from special. 1905 paper. How do we know it's correct? What's the evidence?
Perihelion of Venus.
No, that's that's GR. Yeah, Mercury. That's GR.
So it's the
Do you know the perihelion proof? Do you know what it's all about? Can you explain it?
Well, my understanding is that
Mm-hmm.
if you use the if you use the tensors and the mass of Mercury and the Sun,
Yeah.
you get a you get a correct orbit as opposed to the pure Kepler orbit.
But okay, but what's like? Can you explain Einstein's explanation besides just like the tensors?
No, I'm not aware. I mean, I think the tensors. My understanding is that the tensors are the explanation.
Tensor is just coordinate transformation or something, isn't it? Isn't that?
Well, no, it's also no. Well, it's the force. It's the dynamic behavior of the system. Okay, I have to rejoin FE tests. So
Okay,
I'm gonna.
I'm going there too. Okay.
Okay.
This channel is meant for people to wait in when if Dell has invited people to join the open panel while Dell is live. Even if Dell is on live, if there is no open panel, there is no reason. I was having an actual discussion with Omnivore, but he wants to join a panel. Like, you're barely gonna get to talk in a panel. Why would you want to join a panel? Like, we were doing actual science. No. And nothing is happening. Jesus Christ, what a waste. Okay, anyway. So there's let's look at I guess we have to look at the perihelion. So Mercury, perihelion precession. Mercury's.
You know what? We do not talk about Mercury enough. Like, I know it's not as cool as like Venus or Mars or even any of the gas giants. You know what? We do not talk about Mercury enough. Like, I know it's not as cool as like Venus or Mars or even any of the gas giants either, because it's pretty small and it's so hot and so arid there. But if it wasn't for Mercury, we would not understand general relativity half as well as we do. And Mercury's orbit was actually the very first proof of Einstein's theory of general relativity that we ever had. So when Einstein came up with his new theory of gravity in 1960, his theory of general relativity, he did that through saying, if we can imagine gravity as curved spacetime, any object that has mass will curve spacetime. And the bigger the object, the more it will curve the space around it. So that objects also traveling along that space will travel along that curved path and get their trajectories changed. And he said we could think of planetary orbits just like that. And when he did that, he came up with a whole new suite of equations to describe his theory of general relativity. Now that was all well and good, but it was just theoretical. It's one thing to actually just say mass bends spacetime, but you actually also have to prove that as well. And so Einstein came up with.
Hello? Oh my God, what a waste. Ugh. Wanna continue talking in my VC? Wait, that's not it. This is it. All right, let's continue listening to her. Is she going to actually explain it or meta explain it? Explain as if she explained it. I'm going to wait here for a bit. Okay.
Three tests that you could do to confirm whether this was the case. The first one, he said, would be that stars' positions would change during a solar eclipse. And that was because.
Okay. I don't need general relativity for that. This I can prove either from the aether model, which is based on just looking at an apple falling, or I can base it on Newton's universal gravitational. 1 second. I started tests. Okay. Special relativity is a physical theory that plays a fundamental role in the description of all physical phenomena. As long as gravitation is not significant, many experiments still play an important role in its development and justification. The strength of the theory lies in its unique ability to correctly predict to high precision. Okay. Okay, let's okay. That is weird, but fine. So I don't need GR for this. This comes out of ether directly. It also comes out of Newton directly because the test mass cancels out. So a massless particle from in Newton accelerates exactly the same as a massive particle. And it also comes out of Galilean gravity. Join again. You have to rejoin. Omnivore. We can go back to your server. Hey.
All right.
So okay. Let's make it maybe a little bit simpler. Let's just talk about special relativity. So Einstein wrote in 1905 SR. How did they know it's correct before GR? Let's ignore GR for now. So how did they know? How did Einstein know? What's the evidence that in 1905 and 6, 7 until 1915 before GR? How did Einstein know? How did anyone know SR is correct? How did they know it?
So I think that I would guess that it explained the results of the Michelson-Morley experiment would be one of the key ways.
I can explain Michelson and Morley like at least one more way with my ether. So it's just not
Yeah. Okay.
it's just
well. Oh.
it's just not
Okay. So
it's just not accurate enough. So the ether, according to me, the ether is moving at about 300 meters per second, and they assumed 30,000 meters per second. So they were way off. They would not have gotten a signal, according to me. And my ether model works with everything else, with dark energy, gravitational time dilation, gravitational lensing. Everything works with my model. So
Okay.
okay, so Michelson, look, Michelson at this point is 154 years ago. So we got to do better than that. So I think at this point,
Well, I think at this point we've got general relativity, right? So we are doing better than that.
I don't know. So I don't want to. So I don't know GR, and I don't know how GR and SR are connected. So let's just talk about SR. Right? SR should be able to defend itself. How do we know SR is correct? What's the evidence for SR? Because anything in GR, I can explain with my ether. GR for me, I started from GR. I started from a gravitational theory, and every phenomenon that I'm familiar with fits perfectly. Basically, I don't know anything about the perihelion, so I don't know about that, but I wouldn't be surprised that I can explain it with my ether very simply because I've been able to explain everything else with my ether very easily. Like you don't need any math. It's completely intuitive and mechanical. Time dilation, lensing, black holes, dark energy, everything I threw at it stuck immediately.
Okay.
Like I can explain exactly what a black hole looks like inside mechanically based on my ether. Everything makes sense. There's no infinities, there's no division by zero, there's no infinite density, infinite curvature, nothing. I don't have any curvature. Everything is completely mechanical and intuitive except for a special case in special relativity. One case in special relativity, I think Einstein is wrong about, which completely nullifies SR.
Okay, what one do you think he's wrong about?
So let me show you I think the easiest would be if I would share my live stream with you. So in my side chat, I'm streaming right now because I'm always streaming. So if you go to my stream, and I'll open here the whiteboard. The easiest thing is for you to see my whiteboard in my stream. Tell me that you can basically see
All
my.
right. Yeah, I see your whiteboard.
Okay. So this is the new rubber ducky experiment. This is rubber ducky 2.0. So the original rubber ducky proved that a rubber ducky always measures the speed of water surface waves to be a constant. Okay. Like I told you, everything I threw. No, you don't have to. It would be easier for you to see it in the live stream. You want to see it here? It's not gonna be as easy.
I'd rather see it here.
Fine, no problem. So you can see my mouse, right? But unfortunately, once in a
Yeah,
while,
I see your mouse. Yes.
very soon you're not gonna see my mouse. That's where the problems will begin. It's gonna start disconnecting us. That's like Discord is terrible. Discord whiteboard is terrible, but we'll try. Okay. So this is Rubber Ducky 2.0. Rubber Ducky 2.0 is already two rubber duckies. Now we're talking about actual relativity. So rubber ducky, we have the S prime frame of reference. The top one is a moving rubber ducky. The bottom one is the S rubber ducky. In the S frame, it's not moving. So the S rubber ducky not moving. S prime rubber ducky moving to the right at velocity 1 meter per second. The speed of water surface waves, is 2 meters per second. So this is 50% of the velocity. So you should be getting relativistic effects, right? You're traveling 1 meters per second. The S prime is moving, right? Compared to 2 meters per second, that is my maximum speed. Anyway, so as you can see, S prime rubber ducky has a clock, and the clock is time dilated, right? So let's start
because the clock is entirely because the only thing that the clock can do is time water waves as a single talk. It's not related to anything else.
Look, this is an actual bathtub, and we are humans playing with actual toys in the bathtub. Where we have the top view of the bathtub. These are actual rubber duckies with actual emitter and detector. So everything
I'm
here.
I'm just saying that in order for your statement to be true,
yes,
the clock that the rubber ducky perceives can only.
It doesn't perceive. It just ticks. We're perceiving. The rubber ducky doesn't perceive. The rubber ducky has a clock. It ticks. We're perceiving the ticking, and we see time dilation. We see the clock slowing down as the rubber ducky is moving at 1 meter per second.
Okay.
Do you agree? Right? You see D compared to D prime. Right? D prime is longer. The wave has to travel diagonally until it is detected. So
yes, I understand what you're saying. I am not sure that the perception of time passing works the way.
Ignore relativity. Ignore Einstein. This is just a thought experiment about a real rubber ducky in a real bathtub. Let's leave for now Einstein out of the picture. I'll reintroduce Einstein when the time comes to deal with the contradiction.
I'm not talking about Einstein. I'm talking about the perception of time passing.
There's no perception of there's ticking. There's physical ticking. There's green ticking, and there's red ticking. Right? The S is not moving, so it's ticking. Let's say at 1 tick per second. Let me actually write it down. So tick, let's say.
So in those in that situation, those waves will interfere with each other.
No. There's no. Okay. Frequency equals 1 tick per second. This is
Yeah.
this guy. This is non-moving. S is not moving, and it's 1 tick per second.
Right.
And S prime must be ticking slower. Right? We as humans outside looking from the top of these toys. These are toys. These are baby toys. We're looking at these baby toys. We can see that the S prime baby toy is ticking slower because it's moving at V 1 meter per second.
What we see is we don't see it ticking slower. What we
What?
see is the waves. Yeah, we don't. Yeah, correct.
Okay.
We do not.
But
What we see.
this is a tick.
Yeah, I know.
Okay.
I know. But we don't see the waves moving slower.
This is in the dark. We can't see the waves. It's in the dark. All we see when the detector hits, there's a light, a red light. Tick.
Right.
That's it.
Yes. Okay.
Let's
so
make it.
so then we will see the red light tick slower in that case.
Let's make it. Oh, it's already green? It became green already? Wow. Okay, so it's green. Good. So the top is green and the bottom is red. So this is the red tick and this is the green tick. Good. So all we see is green flashes, where here we see red flashes. So which the green flashes compared to the red flashes? What's the frequency of green flashes? Is it higher frequency or lower frequency than the red flashes? What do you think?
It would be higher frequency than the red flashes. However,
what did you say? I didn't get
it'll
it.
be higher frequency.
Okay. No, what? S prime green is higher?
No, green is okay. So green is a moving one. Green is lower.
Okay, yeah, I agree. I concur. So let's change the color to green. Let's just say, I'll say it here. So F is equal to, let's say, 0.5. Let's say it's 50%. Even at 50% the speed of light, what is it, the time dilation? Is it 0.1? Is it?
I don't know.
All right, let's say it's 0.8. It's about, let's say about 0.8 tick per second. It's not even 1 tick per second. Let's just assume that. Okay. So, okay. Would you say this story is okay? So the we see the top guy S prime ticking slower than the normal non-moving S. So far, so good.
Okay.
Okay. Wait. Are you right? Are you following?
So
Recapping. Go ahead. Yeah.
So yeah. So in this situation where what we're doing is we're counting flashes of light, either red or green.
Yes.
Then yes, in that situation we will see. We will perceive one of them flashing less than the other.
Right. Which is less, green or red?
The moving one is going to be less.
Good. The green. The green is moving. It's going to tick slower. I agree. I concur. Okay. Fantastic. Would you say this is Einstein compliant? Einstein SR compliant?
Meaning what? Meaning that it
moving clocks
explains.
Moving clocks tick slower.
Yeah.
Right.
Yeah, in that sense, yes.
Okay. I concur. Okay, the next step is S is now will be looking at S prime. So until now, S was red flashing. This I call the S's internal clock. Green flashing is green internal clock. Now let me change the color to purple. That's not good. Okay, this will be purple. And this has to go back to green. Good. All right. So the purple is going to be S listening to S prime. So every time S prime ticks, it's going to send out a signal, water wave, that S will detect and flash purple. So far, so good.
I guess. So I'm not sure. I'm not sure what. I know that you're setting up an experiment, but I don't know exactly what you're trying to show. You're saying that
I'm gonna
something.
show Einstein is wrong. 100% wrong. There's no reconciliation. I try to be completely compatible to modern physics, to mainstream. I can't. And I either my ether is wrong or Einstein is wrong. It's incompatible. So this, this is make or break. You want to prove me wrong? This is your chance.
Okay. Well, listen, I think so. What I'd really like to see here,
sure,
is a simulation that shows what you're doing.
Sure, but this is a thought experiment. There's no difference between a simulation and a
I
bathtub.
know, right. I'm not saying that there would be a difference. What I'm saying is it would be clearer to me.
Yes, I agree. That's
what
why
we're discussing.
I agree. I mean, it would be nicer to actually have a toy and play in the bathtub. I agree.
Well, I don't even mean that. I don't mean a physical replication of the
Right, we
experiment.
could
I
do
just mean like
a computer simulation.
a Python program that
Sure. Sure, I agree. I agree. But for now, that's all I got. I got a whiteboard.
Yeah. Okay. All right.
Okay. I mean,
that's. I mean, fair enough.
It's what I have, and look. I'm trying to disprove me. I told you this all along.
Yeah. I understand. I don't think you're in bad faith. I'm not at all saying that.
Okay.
I'm just, so for me, like I have other stuff that I have to do, and my comprehension of this is like, okay, like I think I understand where you're at here.
Okay.
But I'm not 100% sure I do. And
okay.
I've got, like I said, I've got other stuff that I'm working on.
Okay. I understand.
So my ability to consume what is a fairly complicated, thought experiment.
Yeah.
Is like, I'm afraid I'm not getting it.
Look, I understand. I'm just letting you know. This is the part that is compatible with Einstein. This is not this is the setup. The part that's incompatible is when I switch roles and S starts moving. Then this becomes incompatible, and I cannot make it compatible. I've given up. So for me, Einstein is wrong. I cannot show that a moving because of the ether, this is moving relative to the ether, and I don't have any experiment that confirms Einstein either way. As far as I'm concerned, Einstein has never been confirmed. So I don't know what's going on. Like when I start thinking about it, I realize we have no evidence special relativity is correct. It's completely unfounded. So I'm ready to hear what's the evidence for SR. I want to go through all the evidence of SR. If any evidence of SR is like this, then it's compatible with me. So that's not relevant. That's not evidence for SR. There might as well be evidence for ether. If you have any evidence that I'm wrong, that's the end. That should doom my theory. My intuition, I'm right. Einstein is wrong. We can retract Einstein. So
okay, listen. I think we look. I'm not saying this. I think we need to do this in a more formal way because I can't.
Okay.
I don't think I can give you a fair hearing right now.
Sure.
So,
all right. Yeah, sure. I appreciate your time. I mean,
okay. Yeah, and I'd like I would hate to say no, I think you're wrong just because I'm not.
I'm saying if we, the question is
yeah, but because if I'm not able to concentrate enough,
yeah,
then I
yeah,
will say
I
no.
completely
I
agree.
don't get it.
But at this point, I don't care about any thought experiments because my thought
Okay.
experiment and Einstein's thought experiments butt heads. As far as I'm concerned, I'm as correct as Einstein because we both have a thought experiment. So that's useless.
Okay.
And I agree with Einstein that the rubber ducky never can never measure, always measures a constant speed of water waves. So everything is compatible except for this. And I think I'm right. I think there's no evidence Einstein is right. I think the the moving will perceive a faster stationary. Sorry. Yeah. The moving will
Okay.
perceive a faster. It's not relativity. The theory should be changed. Its name should not be relativity. It should be absolutism. Everything is relative to the ether. This is how. So the question is: do we have proof that Einstein is correct in this scenario? I think we have no proof for that. I think SR has never been tested. SR is very nice on paper. It's never been tested, as far as I'm concerned. Like when I think about it, it's like, what is the evidence for SR? It's like there's all these like muons. Okay, muons fit perfectly with scenario one, which is ether compliant. So that's not evidence for SR. That's evidence for either SR or not SR, for absolutism, for ether. All right, so that's no good. So what is the evidence for SR? There's no evidence for SR. What's the evidence for SR? There's no evidence.
So I put in their test for SR.
Oh, you mean in the Wikipedia?
In the chat, yeah.
Look, I don't. I can look it up. I mean, I'm fine. I'm just at this point. This is just from a couple of hours ago that I
So they've got Sadnak. They've got a bunch of stuff in there.
Fine.
But I mean, so
I just need this. I need a moving observer. A moving observer looking at a stationary observer.
Mm-hmm. Okay.
Right, because Einstein says, I am always the stationary.
Right. Well, Einstein says I can always. Okay. All right. Listen, I need to drop, but yeah. Okay. Yeah. Also, you can. I mean, I don't know if you want to, but if you would want to do that, but you could also bring it by, Globe Gangsters and see if people take a look.
There's
at
no
it.
one there. It's empty.
Well, for now, yeah, but a little later in the day,
I'm
I
waiting.
imagine people will be there.
Okay. I'll wait.
All right.
I'll see you.
Okay. Good deal.
All right. Thank you. Let me see. Brian, join voice. Hello? No, nothing. Okay, let me send an email. What's the point of this server? It's such a weird server. It's like, can I... Anyway, let's wait for them. I have to send an email. Hello? 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 If that doesn't work, you may have to wait on Dell. I'll let him know you're all waiting. And this is like from half an hour ago. All right, forget it. Let's look at. I need to share some emails. This is so much work. Oh my god. 1 second. I wish I could pause at least the recording. Let's do this from. You know what? Let's listen to like general news in the background. Still 196. Let me see. Tory party fall apart. Muhammad hijab and condoning terrorism. Planet. Why I quit Twitter. What? Okay, can you talk? Can you listen? Talk. Ti-da-da, la 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 la. Ti-da-da. I can talk on disk. What's a disk? Discord. Yeah. VC. Hey, what's up?
Hello.
Hi. Anyway, so good news and bad news.
What happened?
I think Einstein is wrong.
About what about what specifically?
SR, I'll show you. It doesn't work. I don't know. I'll show you. I don't know. I don't know how to work. How to make it work.
Let me send the whiteboard.
Okay, so it takes a while to explain this thought experiment, and I don't know how to deal with it. I don't know how to deal with it.
Okay, so which one of the boards is that? Is time dilation?
Wait, what?
Which board are you drawing in? Oh yes, it's this one, time dilation.
Yes, time
Just
dilation.
zoom out a lot. So
Okay.
you've discovered the triangulation trick, right?
What's the
The
triangulation
triangles.
trick?
Discovered the triangles.
What triangles?
Yeah, it's like when like Einstein's theory doesn't work very well when you have like, because you have like if you have like two moving observers and the ether is stationary, you have to correct still. There's some stuff like that, and you'll get the triangles. You get the triangle from
What?
that
What triangle?
Okay, it's hard to explain here, but if I would draw it, it would be easy to see. But just tell me what
Okay.
you've seen. It seems more or less the same thing.
Okay.
Like,
Okay, so I'm going to explain it first from here. So what we have is the S rubber ducky. I'm at the bottom. And we have the S prime rubber ducky. So in this experiment, the S prime rubber ducky is going to be moving and the S is going to be stationary. But the point is they're very far from each other. So let's say this is 10 centimeter big. This is 10 meters. The distance between them is 10 meters. And this is the other guy. All right. So S prime is tiny over there. It's like a big pool. It's a big bathtub. It's a 10-meter bathtub. A tiny toy is over there. A tiny toy is over here. This toy, S prime, is moving to the right. S prime is moving to the right. S is stationary. Okay, the point is they're very far from each other.
All right.
They're 10 meters apart. Okay. So my point is that these are straight lines. They're both right. This is 10 meters. They're 10 meters apart. Anyway, so we have the S.
Yeah.
This is the S rubber ducky. This is the moving S prime rubber ducky. So this is the S prime rubber ducky moving to
Yes,
the
and
right.
you want like a clock. You want like a clock, right?
I want like a clock. What do you mean?
You want a clock between them with pulses.
Let me just write here.
Alright.
Time equals 1. Time equals 2. Time equals 3. Okay. So this is S prime. S prime is moving through the water. The green ticks is the S prime ticking. The red ticks is the S ticking. And the purple tick is the S seeing the green ticking. So when a green ticks, a wave travels to the
Okay.
S and makes a purple tick.
I see.
But remember, there's 10 meters between them. So this is not to scale. Each one is tiny. Each toy, rubber ducky, is tiny. The distance is big. So there's no Doppler. This is the Doppler shift. There's no Doppler shift. We're ignoring Doppler. That's not what it's about. So far, so good?
Yeah.
Okay. So I'm going to turn off the lights, right? This is a bathtub. I'm turning off the lights. So we can't see anything except for a green LED, a red LED, and a purple LED. So far, so good?
Absolutely.
Okay. So, first question. So, assuming red ticks at 1 tick per second, how fast is green going to tick? Faster?
Okay, so they're supposedly the same, right?
Yes, they're identical toys. Speed of water is a constant, 2 meters per second. Velocity of S prime is 1 meter per second.
Okay, so wait, what specific velocity? What specific difference will there be? Okay, so the velocity of the water is 1 meter per second, right?
Velocity of water is 2 meters per second.
Oh, it's 2 meters per second. You have it as 1 meter per second. So
The
so
water.
what's 1 meter? Oh,
The
yeah. Okay,
water.
so C is 2 meters per second,
The water is.
and the velocity of the tank is 1 meter per second. Okay, so I don't know what's the distance between the these are like rubber ducky clocks, right?
These
So
are
what's the
rubber.
distance between? Is it 10 centimeters? The distance between the two clocks. So yeah, it would be like you already have it there. You have it as 0.8 ticks per second.
Yes. Do you agree?
But yeah, I was just trying to understand the whole setup.
Yeah.
Yeah. Okay.
So you see here,
So
you see the time dilation of the moving S prime. You see D prime compared to D. So D prime is longer.
yeah.
So you see that S prime is experiencing time dilation. You there?
Okay, so yes, yes. So what's the
So we're
what's
looking.
the issue?
So we're
now?
looking. The lights are off. There's green flashing, red flashing, purple flashing. So we said red flashing is 1 tick per second. Green flashing is, let's say, 0.8 tick per second. It's slower. But what's the purple? How fast is purple flashing?
Okay,
Ignoring
good
Doppler.
question. So purple is 10 meters. Well, that's a lot. That's gonna take a long time to go from.
But I'm not asking how much
But
time
but
between.
yeah, it takes to start. You're not asking that, right?
Right.
You're just assuming that at t equals to 0, there
So
was some kind of pulse reaching
right,
it, right?
right. So the pulses are about to
Okay.
reach. The pulses are about to reach S. So S is about to be bombarded by the purple ticks. So
Okay.
we don't care
Good.
about the 10 meters, except for it's a straight line. There's no Doppler shift. So
Okay.
given that the purple is ticking right now, the red is ticking right now, the green is ticking right now. We said
Yeah.
already red is 1 tick per second, green is zero point 0.8 tick per second. What is purple tick per second?
Interesting. Purple should be it. Shouldn't it be like 0.9 or something, or maybe it's 0.8 as well? Let me think about it. Yeah, it should. Wait. So only one is moving. So and okay, so it ticks every time it. So in this case, it's a little bit different because it ticks every time it receives something. So in this case, you're saying that
That's my. I'm
it's
giving you.
0.8
I'm
per
not
second.
saying. I'm giving you my opinion. You tell me your opinion. I don't care. You
Yeah,
don't.
I'm thinking about it. Yeah, it seems like intuitively just seems the same, but I'm trying to think about it a little bit more to see if I'm wrong. Um, so why there be a difference? So we imagine the two moving at the same time, right? And this is like the same problem I was thinking at the beginning.
Hmm.
Because if both of them are moving at the same time in relation to the ether, it's the same thing as it's the same thing as one is moving with the ether and the other one is moving against the ether in some way or in a different speed than the ether. So in this case, there should really not be a difference at all. Like I don't see why there should be a difference
Okay.
between one and the other. I
So
really don't. I'm thinking about why there should be a difference. If I'm wrong on something, trying to visualize things, but I think it's the exact same.
so you agree that if green is zero point 0.8 tick per second, then purple is also zero point 0.8 tick per second.
Yeah, it's just gonna take a long time to start.
Sure, that's
Yeah.
given. Okay.
Other than that, it's the same.
Okay. I agree. Okay. And this, would you say this is Einstein compliant if we switch to light?
No, it's not Einstein compliant at all.
This is
And
not.
that's the same problem. I've seen the same problem of. No, this is not.
Why not?
I've seen Distinti pointing out this problem.
What did you see?
Um,
What?
I mean,
What did you say?
if you take this to a different setting, to a slightly different setting, in which there are two rubber duckies, and they're both moving in
No, no,
relation to the
no,
but okay, so
no,
this one
no.
just specifically, yeah, you could still interpret this one specifically with Einstein.
Right. So
Yes, you could still.
Einstein says if S is the observer, then S
Yes,
can.
and then what you do next is like you put two green dots, right? Yeah,
Wait,
I
wait,
see.
wait. I'm just saying if this is now rubber ducky spaceships. Now let's move to rubber ducky spaceships. So the S rubber ducky can claim I'm not moving. So this is Einstein compliant. So from S perspective, S sees S prime moving relative to it, right? S is perceiving S prime moving. So S perceives S prime's clock ticking slower. So S sees a moving frame of reference clock time dilated. So
Yeah.
this is this is Einstein. There's nothing special. This is Einstein.
Yeah, but if you make a certain change, it won't work. And I think that's what you did.
Right. So the next step is reverse. So now we're going to move this S rubber ducky to the left. And S prime is stationary.
Prime is stationary.
And the same
Okay,
question, let me
so
just change the color to
yeah, that's
purple.
purple possible.
Yes.
Okay. Yeah, so this one's gonna take. Well, but you can just claim that. So in this case, you're saying that the S prime is stationary in relation to the median, right?
S prime is stationary. So
Yeah, but
V
in this
equals 0.
case, in this case, it still works or not?
Let's just say that the frequency is equal to 1 tick per second.
In this case, it still works, right?
I
Or
don't
am I
think so.
missing something?
I don't think so.
Okay, wait. Let me think about the red one. Okay, so in this case, in this case, it's going to be S is not going to be 1 tick per second. S is going to be the 0.8 ticks per second,
Right.
and the other ones are going to be the 1 tick per second, and the the relative one is going to be 0.8 ticks per second, or not. That's the issue, right? Because that one now is going to take a little. Was that one now is going to be 1 tick per second? Yeah, that's one now is going to be 1 tick per second. Okay, so that one's 1 tick per second. Okay, it still works because the proportions are the same.
But is this Einstein compliant?
Oh, okay. So
because notice that if S claims that it's not moving, right?
And the other ones don't actually. It's not like the other ones. It says that's actually experiencing time dilation.
So 1 second. Let me just say this. So this is not Einstein compliant because
Yeah, that's not Einstein compliant.
wait. Let me just say it.
Uh,
Hold on. Let me just say it so
Okay.
we agree or disagree. So this is not Einstein compliant because according to Einstein, S can claim that it is stationary, but S is ticking very slow, meaning S's consciousness is very slow. You can imagine that this is 0.0001 tick per second if V is very fast. If V is almost C, then red is ticking very slow. But this is ticking normally. So S now looking at S prime, S thinks S prime is moving just like before. According to Einstein, there's no difference from the top one.
That's not even Einstein. That's just regular relativity, classical relativity.
Hold on. 1 second. So S, according to Einstein, S can claim that it is stationary. It's not moving. And it is rather S prime that is moving. But however, S is observing S prime ticking super fast. This is a complete violation of Einstein's relativity. But this is
and there's another one. There's another one that you can. Yeah, that's even more simple than this. It's just like even like if you have two different uh, if both S and S prime are stationary in relation to each other, but they're both moving in relation to the medium, you will still have the same problem.
Why? They're both slowing down just at the same rate. That's not a problem.
That's not a no. The problem isn't that. The problem is in the purple one.
No, no, there's no problem.
No, the problem is wait.
If they're both moving at the same
No,
rate,
no. It's not. It's not a problem if you look at this like that. But if you look at how long the light takes, for example,
it doesn't. We're not looking
in
at that.
relation.
We're not.
Yeah. But that's another problem.
No.
Because if you look
I'm
at how long
ignoring.
the light
No,
takes,
I'm no.
that's
No, I'm ignoring
yeah.
that.
No, now you're ignoring that.
Well,
But that's an important thing
no,
in
it's not.
relation to relativity.
No.
No, it actually is.
Okay, look,
But in another context. Okay, we'll talk about that later.
sure. So this is this is a violation of Einstein's relativity. So Einstein claims that he can just switch frames of reference nilly willy, which is complete nonsense. That is complete nonsense. You cannot switch.
Yeah.
Right?
Another thing that you could do that's even also simple is to add some acceleration or some forces.
No, I don't want
Yeah.
to. No. I don't want to. No.
Yeah.
This is just good old special relativity. Einstein's proclamation that you can nilly willy change frame of reference is unfounded and it's incorrect. And when you think about it, has Einstein ever been proven correct? That's the question. What is the evidence that we have that Einstein is correct, that SR is correct? How do we know special relativity is correct? Everybody always says,
it makes some predictions, but it's never been proven correct, obviously.
what predictions? I mean, it makes predictions. What prediction has been tested? What SR? Where?
For example, the GPS thing, they use that.
The GPS, I can
general
explain. The GPS is not. I can explain with aether. The GPS.
Yeah, think about those claims, but people will tell you that is that GPS is too simple to prove something
No.
as old
GPS.
as relativity.
No. GPS is gravity, and I can easily explain gravitational time dilation. So GPS, I don't care.
Yes. The thing is, many theories can explain GPS, but there's no. That's my point. Like, there's no specific proof for general relativity.
Right now, I'm comparing my ether model to Einstein. My ether model works with every phenomenon I've looked at, except for this. But this is not a phenomenon. This is Einstein's thought experiment. Where is the evidence that Einstein's thought experiment is correct? Where's that evidence?
If I was going to look for stuff like this, you'd probably want to look in cosmology, but it's very hard because they do assume that the Earth is stationary, right?
I mean,
but the problem is they also measure distances using assuming GR.
Look, the problem is we need a symmetry breaker, as they say in debate. So I need an example where my ether contradicts Einstein. I need.
So I'm thinking about how you could get that.
Right.
Okay, so imagine you have a star, and you're assuming that no, but it's going to be problematic because the ether will likely have different speeds in different places, and it's probably just all going to sort of even out.
So as far as I know,
but maybe you could maybe you could try to get some clue for what the speed of the ether is. I think there was like
no, so I spoke to someone and right away he said, well, Michelson already proved there is no ether. So I told them, listen.
No, but wait. I'm getting some.
Yeah.
Like, for example, try to see some kind of shift in the cosmic background radiation.
How's that relevant? How's that?
uh,
What? You're breaking up. Are you in a
because we
tunnel?
can, if there's some kind of shift in those in that radiation, we can assume that's some kind of movement in the ether. You agree with that or not? Are you there?
Yeah, I'm here. Uh, the simplest the
Yeah,
simplest
do you
proof.
agree with that or not?
I don't know. I would have to think about it. I don't know. Like that's
No, just think about it for a bit.
look,
Like
we're
if we
trying.
see some kind of shift in some kind of directional shift in background radiation, that would give us a clue about what the speed of the ether is in your theory, right?
Look, I have and I have experiments. I think I'm rethinking my interferometer, and I think maybe my interferometer would be able, after all, because I don't think there is length contraction.
It could be. The question is if the question. No, there is length contraction. I can demonstrate length contraction. It's very simple. I will do that if when I get home. I don't want to draw you on the phone.
But the question
I
is,
can do that when I get home.
the question
No, length contraction is very simple. It's kind of you remember dialects
wait,
video of
wait. No, no, no. What I'm saying is, no. The question is, according to the ether theory, I mean, once you have time dilation, I think you can get length contraction.
yeah, that's same in answer.
So I'm saying, okay. So if the question is, so but this would be Lorentz length contraction. So it's a physical contraction. The electron, the electric field, the photons, right? Because if we're assuming, right, we're looking now at the quantum foam.
Yeah,
When
that could be. Sure.
when you look at the quantum foam, the photons now move slower. So the interaction between electrons, the repulsion between electrons is weaker. So
Yeah.
you get length contraction from that.
Yeah, the question is, we should distinguish that type of length contraction from the length contraction that's just apparent length contraction, right? We still need to do that.
So I don't think there is apparent like relative length contraction.
Don't think there is one. So that's the one you don't think.
Wait, there.
But
So
but that can. But that one isn't that one just like a consequence of moving frames?
right, there might be so is there time dilation because of moving frames?
No, it's because of the ether moving.
No, but okay, assuming ether, right? Let's assume
It's
ether.
the same thing. But wouldn't length contraction just be the same thing?
Wait, assuming ether.
Because
Wait, assuming ether. Do you okay? So we have physical time dilation. Do we have anything besides physical? Right, we know the clocks are ticking slower. Is there a nut? Is Einstein still relevant? I mean, we have actual ticking slower. I mean, the clock we can, if we assume ether, then the clock is ticking slower. But there's no ticking slower besides that. The ticking is already accounted for. So there's no, I don't think there's any further ticking slower. Like Einstein is not relevant. Once we assume ether, Einstein is garbage. Einstein said nothing. Einstein gave us a mathematical postulate. So he just said, assuming the speed of light is constant. Well, I'm assuming the speed of
give an argument.
so I'm assuming the speed of the water waves is a constant, and I actually have proof. I can explain why each rubber ducky perceives the speed of water waves to be a constant. So the speed of everybody measures always the same speed of water waves. So I don't need Einstein. So I throw Einstein to the garbage. and all I have is actual time dilation. That's all I have. Therefore, all I have is actual length contraction. That's all I have. So,
Yeah, wait a minute. Let's think about the length contraction
no.
as an apparent length
So,
contraction.
so
But I get what you're trying to tell.
no, I'm saying so the interferometer is actually, so if the interferometer is going to detect time dilation because of, because interference pattern because of time dilation, it probably will also experience length contraction, and they're probably going to cancel each other out. And I think this is what Lorentz invented, and Einstein is Lorentz compliant because Einstein arrived at Lorentz equations for different reasons. But if Einstein agrees with Lorentz transformations, that means that Lorentz agrees that physically you can never detect the ether using an interferometer, which that's my intuition.
No, that it doesn't imply that.
Wait, what? That's what
Because
Lorentz.
no, it doesn't imply the final conclusion.
As far as I know, Lorentz created Lorentz transformations to explain Michelson's null result. And
Yeah, but
Lorentz
then you
and Lorentz transformations are Einstein's transformations. So much so that no one calls them Einstein's transformations. Einstein derived his transformations, but everybody calls them Lorentz transformations, even though they have nothing to do with each other. Lorentz transformations is why, like, assuming Michelson got a null result, assuming, what would the transformation look like? And he gave us time dilation, length contraction in order to give us a null Michelson result.
right.
Einstein didn't do that.
Okay.
Einstein just, let's assume the speed of light is a constant, which also is sort of like assuming Michelson null result, maybe. But the point is, we don't care. I don't care. Einstein uses Lorentz transformation. So when you say Einstein is correct, you're saying Lorentz is correct. And if Lorentz is correct, then the interferometer will always give you a null result. And we know Lorentz is correct because Einstein has been tested, so called.
Okay, but wait a minute. It also depends on how you set the interferometer.
No, Michelson.
Like,
Just a
if you could
Michelson.
rotate the interferometer, yes, the length would contract. But how would you? Yes, you would then not be able to measure it. Still.
Right. Which is fine. I'm fine
Yeah.
with that.
You'd never really be able to measure.
Exactly.
I'm thinking. I'm visualizing the whole thing. Yeah, there would be no way to actually measure it. Yeah, that's interesting. It did. Because if you, because how would you like make an experiment? Like you'd have to, because we have another problem here. Like should like wavelengths also contract? No, like the wavelengths of light, should they also contract accordingly? In this case, yes, right?
What do you mean contract?
Yeah, it would be kind of like a Doppler effect. And it's
I
like
mean,
the arm of the interferometer. We can like not have an arm. We can just have light. So that's why. So we could still like find a way with that. But if the wavelengths actually contract as well, then we can't. And that should happen with the ether theory.
what? What did you say?
That's interesting stuff. Yeah. You not change the color because the frequency will change accordingly.
What?
So that would not be much of a problem. But
Are you there?
You should squash the waves.
What?
You should squash the waves if there is a direction of movement, you should squash the waves.
I mean, who's moving? Like if I'm
Huh?
moving,
No. If the direction of movement of the ether,
I
if the
don't.
ether is moving.
But that's not. But that's Doppler. I don't care about Doppler right now. I mean,
No, but that would be measurable in interferometer, right? Like if you can somehow. Question is
no.
if it all evens out. Like it's still going to even out in the end. Because if you send them here, then they just send this one. No, you'd still be able to measure it because if you send think about it, if you send waves against the ether, you would still be able to they would still go slower, so you'd still be able to use an interferometer. It's just that you just want it to be made of basically light and the reflector and the vectors.
Wait, what?
Question is measuring the. No, you'd still be able to have an interferometer. Yes,
What?
that's one way that works.
Wait, you can. So you're saying the interferometer should give a positive
Yeah,
result?
it should still work.
Positive result?
You might have to do it a little bit different, but it should still work. Like you send a wave from, like for example, in one beam you send a wave from the bottom, and you reflect it back. And in the other one you send the wave from like sideways, and then you reflect it to the same point of the other one, so like a 90-degree angle to for them to interfere with each other. And you should still find some direction in which like there would be different interference patterns. Still, if you rotate the experiment, you should still find different interference patterns.
So hold on, slow down. I'm trying to understand. So you're saying we should be get
Right, if you want.
no. Let me just ask you a question. So you're saying Michelson's interferometer should give us a positive result?
Not the way he did it, probably. I mean, it should still. You could get a positive result from the way he did it, but the best thing to do would be to rotate it.
Michelson's experiment is rotated. It rotates. It's a floating table.
I mean, but it rotates with the Earth, so it's not
No, no,
great.
no. Michelson is floating on Mercury. Michelson is
Oh,
rotating.
that's the later one that he did, right?
No, that's the original. The original is it's
It's worth noting one thing that Michelson Morley didn't get zero result. He got what they call a null result, right? So he got a
no,
result, but it
no.
was too low compared to what he was expecting. No, yes, that's true.
It's look,
No, these are facts.
it's null. It's under.
No, no. That's just that's now we're discussing semantics. Let's discuss what he got in reality. He got a result, just not the result that he could explain. So they considered it a null result.
He got.
Like because you have to see how this is set up. Like what's the framework? Like there is an hypothesis, and there is a null hypothesis, right? Yeah. Like there's a hypothesis and the counter hypothesis basically. And if you don't confirm the hypothesis in the experiment, then you default to the counter hypothesis, which is the null result. That's what
Look,
the null result is.
look. I
But
saw.
he got a result. It's just not a result
Hold
that
on.
was in line with his theory,
Hold on. Hold on.
with his prediction.
Hold on. I saw his paper. I saw the data. His result is lower than the noise. It's under noise. It's
Lower than what?
noise. it's under
Lower
the
than noise.
tolerance of the equipment.
Okay,
It's
but
noise.
but did he get some kind of cycle? Because you can deal with noise. That's not. It's not. That's not.
The cycle.
It's not the
I saw
issue.
the cycle. It's like I'm looking. The cycle I'm looking for is during the rotation. Anyway, it's
So did
under.
he get any cycles, or did he get anything
Look,
like that?
look.
That's what
It's
I'm
not.
asking.
It's not. It's look. Let's just assume he got a null result. I don't want to
Now
argue.
let's not assume things that might not have happened. Like,
Look,
did he get cycles? Did he get
I
patterns?
don't
Did he
know.
get
I
anything?
don't know. I don't know. I'm saying let's
He
assume.
did get. Okay, but fine. But I don't want to assume that. Like,
Look,
but
I want to prove. Look, it doesn't matter. I mean, what's the point of saying? It doesn't matter what we say. Who cares what we say? Like we can say whatever we
then,
want.
yeah, we can say whatever we want, but we should try to be consistent with reality.
As far as I know, he got a null result.
And it's it doesn't mean much, but okay.
Yeah. Look, he for the rest of his life tried to figure out how he got a null result. So he was very
He
upset.
made a lot more. He made a lot more experiments, and he got positive results in some of them. It's actually true. He just couldn't quite figure out what was going on. Also, he got poisoned with mercury, so he kind of went insane. Yeah.
Okay, it doesn't
There's
matter.
that.
Look, the point is
It kind of matters, but okay.
the point is um I'm asking a question. What is my evidence? One second, let me just text somebody something.
What is your evidence for what?
What is the evidence for Einstein 1905? What's the evidence for Einstein 1905? Just
And there's evidence. There's not absolute proof, but there's evidence. Sure. Again, if I was going to try to test Einstein versus your theory, I, we'd really have to look into like astronomy for this. You there?
Yeah, of course.
So let's say there's a planet and the Earth circle.
No. Look, as far as I know, Einstein's SR has never been tested. It's very nice, they say it's the most tested theory ever. It's the most tested, the most predictions, the most it's never
not the
been
most tested
it's
theory.
never been tested. It's very nice, I can say my theory is the most tested in history. That's very nice. It's never been tested.
I mean, but like let's not concern ourselves with.
No, the point is Einstein is just a thought experiment with no evidence. GR is fine, but GR I can easily explain with the ether. GR is easily explainable with any experiment you show me with GR, I'll explain it to you with ether. So that's not a symmetry breaker. So the question is, has SR been tested? Show me the tests for SR. Show me a single test for SR. What's the test?
You'll not find a test that disambiguates all theories or possible theories versus GR. That's in SR. You will not find a test that disambiguates all possible theories versus SR. That doesn't exist.
Wait, I will not find a test that what?
That disambiguates all possible theories that can explain
I don't need.
the phenomena we're looking at.
Right, but
versus SR.
my question is, show me the tests that
I'm saying there isn't one.
No. Show me tests of SR. Has SR ever been tested? They keep saying it's the most tested theory in the history of the universe. Okay, could you show me a single test? When was SR ever tested?
Ask ChatGPT, by the way.
Hold on,
maybe you'll get something.
I need to log in into something. Give me a second. 1 second. There it is. 1 second. Like when I saw this last night, I was so upset. I said, I must be wrong. Well, I must be wrong. But then I was thinking, wait, who says Einstein is right? It's like, who says, what's the evidence Einstein is right? It's like, very nice. Einstein, blah, 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 blah. Okay, who says he's right? What's the evidence? There's no evidence. It's just stories. Nothing but stories.
It's worth noting that Einstein is mostly theory. It's really not.
It's not
like,
even a theory. It's just a
not
postulate.
like Newton. Newton has a lot of observation.
Right. Newton is based on data. Einstein is not based on data.
Yeah.
What is the data? What's the data for Einstein? It's just a thought experiment.
Did you ask ChatGPT?
No, let me just let me give me a second. Okay. One second. Okay, let me just take a snapshot of my screen. It's like you would think, oh, SR, oh, it's the most tested, most schmested, most bested, quested. Well, yeah, it's fantastic. It's just the best thing since sliced bread. Yeah, it's not. It's never been tested. It's just an assertion. That's all it is.
You'd be surprised how many theories are like that, I guess.
Yeah, it's like you don't want to know.
What? Neuroscience?
Yeah, it's like
I have a notion.
It's like people.
Those stories that like lobotomies and so.
Yeah. When you hear the stories about lobotomy, it's basically nothing. Basically, nothing has changed. It's like total nonsense. Anyway.
Things don't change that much. No.
Anyway,
No,
let me.
the personalities that that make those things happen keep going.
Okay,
They keep
so
being on top. It's like, oh, we were wrong. I'll try again, I guess.
anyway, I mean, don't forget, like most intellectuals are communists. I mean, these people.
Okay, I don't think.
What?
I don't think that's a connection we need to make.
No, they're idiots. What do you mean? Communism is.
No, okay.
Communism.
You wanna go with that?
You're going to ignore that?
No, yeah, we wanna go with that.
I'm
I
saying.
think all political ideologies are idiotic, but that's fine.
No. Einstein was an idiot when it came.
Einstein was a socialist.
Yeah, it was a socialist, a communist, and a pacifist. He was against, going to war. Like an idiot.
I'm against going to war in general.
Yeah.
I'm not against like going to war in all possible.
Nobody wants to go to war.
things, but-
Who wants to go to war? But sometimes you have to go to war. Anyway, let me
Yes.
ask. I'm gonna ask ChatGPT. So, what is the evidence for SR? Special relativity SR proposed by Albert Einstein 1905 has been confirmed by a variety of experimental evidence over more than a century. The key predictions of SR such as time dilation, length contraction, invariance of speed of light. The invariance of the speed of light is not a prediction.
Okay, that's all
That's
good.
like
Okay,
he assumed it after everybody noticed it. It's not a prediction. Have been
And by
tested.
the way, there have been tests for that they're not very they don't show that it's invariant. By the way,
And also I can prove the speed of light is a constant. I have the advantage. The ether model actually has an advantage in this respect. Have been tested and confirmed. I mean, across
I
many.
mean, what you can prove is that it's independent from observers.
Anyway,
from
anyway,
those ones.
okay,
Yeah, that's
many
what you can.
different. Okay, below
Yeah.
are some of the most important pieces of evidence. 1 second.
So it's probably going to talk about like how particles
Let's see.
can be
What is
observed.
listen, you're gonna love this. What is number one? Number one on ChatGPT list. Number one on ChatGPT list, SR is correct. Number one.
GPS.
No. Take another
Huh?
guess. Take another guess.
Not good at guessing. Uh, number one, like clocks, atomic clocks.
No. Number one. Number one on ChatGPT. Number one. Number one on ChatGPT. Number
Oh,
one.
Michelson-Morley experiment.
Michelson and Morley, the
Yeah,
biggest
how did
joke. The biggest joke in the world. That's exactly what Lorentz explained. How could you say that's confirmation for Einstein? That's a completely non sequitur. That's a completely disambiguation. It's like basically everyone can ether easily explains Michelson and Morley's experiment. This is and it's an experiment. They say 1887. As far as I know, it's 1870. This is
Yeah,
almost
but even if you would assume that this proves it, it still don't prove Einstein's theory.
I mean, but it's over 100 years ago. This is what you have to show. This is your evidence. What are you nuts? Anyway, first one, second one. What do you think is the second piece of evidence?
GPS or atomic clocks?
No, try again.
No?
Try again.
Particles.
Yes.
Yeah. Okay.
Which
So
particles?
I,
Which particles?
muons.
Yes,
Probably.
the muon lifetime. Again,
Yeah.
easily explained by ether model. Oh my god.
Yeah, that one is explained by many things probably.
All right, this one, number three.
I mean, it's not even really explained by Einstein. It's consistent with Einstein. There's a difference.
Okay, the
That's a
next one.
significant
The
difference.
next one might be difficult. Relativistic mass, particle accelerator.
Relativistic mass. Okay, no, that one is not very difficult. That one is very easily that one is actually very hard to explain with Einstein. It's just an observation.
No, I mean Einstein
Like relativistic mass is like inertia, like the inertia goes to infinity as you approach the speed of light.
Why? Why?
Yeah,
Why do we get?
But
why do we get it? Why does it
I
happen?
mean, it didn't explain that. It's just.
But how? I need to be able to explain it. How does ether? How do we have a mechanical explanation for relativistic mass?
I mean, if you think about waves, it's like that. Like for example, when a plane gets near the speed of sound, there's a sonic boom, right? Like there is you get a lot of pressure against the plane. It's very hard to accelerate it. You can say that you know that the plane still accelerates. But if you think about something different, if you say that we're all waves in the ether and not necessarily something else solid,
No,
then we wouldn't be able to accelerate
no, you're able to
without.
accelerate. I mean, we know that we're able to accelerate, but these are
No, we aren't able to accelerate past the maximum speed of propagation in the medium.
yes, that's true. But why would it be
Yeah,
okay?
it'd be what?
But why would you get a relativistic momentum?
Relativistic mass is just that. It's just the inertia increasing to when you
So
get
I
near the
would
speed of light.
so first of all, we agree that you cannot accelerate any particle beyond the speed of light because it's a wave, so something has to block it. Something has to, so
Yeah,
intuitively.
it's also it's also again the dynamic is more like in a solid than in a liquid. It's like it's like in something that keeps its structure.
So first of all, intuitively, a wave cannot go beyond the speed of the wave. So something has to stop it. And it makes intuitive sense that it should be asymptotic. And we would experience it, right? We would experience it as like we're pushing and pushing and pushing. It's pushing us back. We're unable, but the energy has to go somewhere. So
Yeah.
it makes intuitive sense. So okay, so ether easily explains that. That's not a challenge. Okay, next.
Yeah, that's okay.
Okay, next. GPS.
Okay,
GPS is
we
easily,
already talked about.
yeah, gravitational time dilation comes out of the ether instantaneously, much faster than it comes out of GR. You don't need to know any math. Next, relativistic Doppler effect. What is that? What it
Okay,
tests?
that's got okay. Wait, that's got nothing to do with. Yeah.
Let me see. What it tested. It's called the Eve Stilwell experiment. Was
No,
designed to
that's well tested. That's well tested, but that doesn't show much of it.
wait. Let me understand the test. Was designed to test time dilation by measuring the Doppler shift in light emitted from fast moving particles. Okay, fast moving particles move through the ether. All right, so they internally their internal clocks slow down. SR prediction: the relativistic Doppler effect should differ from the classical Doppler effect due to time dilation. But I agree that there is time dilation, so that's useless. Next time, lifetime of fast moving particles. That's easily
Okay,
explained.
wait. Let's go back to that experiment.
Which one? Doppler?
The previous one.
Eve Stilwell?
Yeah, yeah. That.
Why do you need to? What's
Okay, so how did he measure that time dilation?
what? But it's not important.
How did he measure that
I
Doppler
I
effect?
don't care. Look, I'm looking for a symmetry breaker. I'm looking for a non sequitur. I'm looking for something that makes a distinction that is that is
Okay, yeah,
disambiguous.
that didn't make a distinction.
So there's no distinction. Next one. Lifetime of fast moving particles. That's that's time dilation. So ether explains it right away. Experiments with light. Fizeau experiment. What it tested. Fizeau measured the speed of light in moving water to understand how the motion of the medium affects the speed of light. SR prediction. The speed of light is independent of the motion of its source, and light moves according to the principle. How is that even related? I don't see how that's relevant.
Yeah, that doesn't
Okay.
explain it.
Relativistic energy E equals mc squared. What it okay. Um Predicts that mass and energy are
I mean,
equivalent.
you can have can use relativity to reach that, but it's not
Look,
necessary.
look, E equals mc squared comes out of the constant speed of light assumption. I have my
Yeah.
ether predicts a constant speed of light, so theoretically it should predict E equals mc squared.
Yeah, that doesn't distinguish.
Right. So as
So
long
the Fizeau experiment is could be kind of interesting.
we'll come back to it. We have more to
Uh,
go through. Hold on. So
but
just E equals mc squared. I'm just saying. So as long as I am looking at a fast moving object, as far as I'm concerned, it's moving through the ether. So it's always been tested. No, E equals mc squared. No, that's not moving. That's an inertial frame. That's like it's non-moving. It's a rest energy. The rest energy is mc squared. Um. Well, I okay. I'll ignore that for now. For now, because it's based on the constant speed of light, which I predict, which the ether predicts as well. Number 9, tests of Lorentz invariance. that's that's like the ultimate proof of the ether because Lorentz was based on ether. So that's meaning. Okay, cosmic ray detection. Same problem. The cosmic rays are moving relative to us, so they're moving relative to the ether, so you're going to get the same conclusion. So there's no symmetry breaking. Look, there's no way to disambiguate. So the only experiment that I can think of is detecting the 11 kilometers per second flow of the ether into the earth at the surface of the earth using a vertical particle accelerator. Maybe that will work. A vertical particle accelerator, if you're throwing particles towards the earth at around 11 or 11.2 kilometers a second, so those will die the fastest. If the particles are accelerated to less than 11 kilometers a second or more than 11 kilometers a second, they're going to take slower. They're going to decay slower. And you're going to see a bump in the test at around 11 kilometers a second. That's the only test that I can think of.
all right. So
I cannot think of
I
another.
guess we concluded this topic. An interesting one. So yeah, we reached our conclusion that you can have that you finally have a disagreement with the mainstream physics.
The question is,
Yeah.
according to me, so if I am moving relative to the ether, I should be able to see a stationary clock ticking slower. That means Voyager, right? But Voyager is moving very slow. But if we could send,
No, it didn't work.
if we could send a fast moving clock and communicate from Earth,
That's GPS.
no, GPS is well explained using gravitational time dilation. So that's not a solution. I need to move through the ether.
You need two clocks, and then they move in relation to
You
each
see,
other.
the problem is that
You need to
the
send two
GPS.
clocks to space, and then they move in relation to
No,
each other.
you don't have
Yeah.
to. You need one clock in
Now
space,
too.
but it has to move fast relative to Earth. I don't think.
Now because the Earth can be said to be stationary in relation to the ether. Now you need to.
Look, our clock are basically not. Let's assume our clocks are not moving. If you send out something really fast, send out something that is moving fast relative to absolute space, like in the interstellar space, like Voyager. Send out a fast moving Voyager, you will see, so we will see its clock ticking slower, but it will see our clocks ticking faster.
Okay, but isn't that what happens in GPS? Which one sticks slower?
According to Einstein, if two clocks are ticking past each other, they're moving past each other, they should each be able to say the other one is ticking slower. But according to me, there's absolute space. There's absolute ether.
Yeah. Oh yeah. Right. It will work.
So one should be. We need to we need to come up with a theory. What is the ether doing? So according to me, the ether around Earth is moving at 11 kilometers a second towards the Earth. So if you send a spacecraft that's moving fast relative to absolute space, relative to the average, like whatever, interstellar space, interstellar or interplanetary, where basically we can assume, based on the ether model, that the ether is not moving. Now, if we're going to
Yeah, but that would be like your. Wouldn't that just be your first case?
No, but I want to send out. It's going to send. It's going to. Its clock. We will see its clock ticking slower and slower and slower. That's fine. The faster it
Yeah, but
goes,
that's compliant with
yes,
Einstein. That's fine.
yes. But it will see our clock ticking faster and faster, and that's a violation of Einstein.
Yeah.
Because according to Einstein, it should be able to say that exactly what we're able to say about it. It should be completely symmetric because each frame of reference is stationary. Each frame of reference, each inertial frame of reference should be able to say, I'm inertial, I'm stationary. I say no, there is ether. Everyone is moving relative to the ether. And this test has never been done. We've never sent out anything fast that is looking at us and reporting back to us. How is it seeing us? This test has never been done. So SR has never been tested. This is nonsense.
Yeah.
Nonsense.
I'm thinking
Absolute
about
nonsense. What?
I'm thinking about what you should see. Like you could, yeah,
You
you
have
could
it.
try to map
You have
like.
it. You have it on your screen right now. You have it
Yeah,
on
yeah,
your
yeah.
screen.
But on a satellite, it could just go around the Earth really fast.
Look, as
That's kind of a problem because like how would you do that? Like satellites, they're generally geostationary, they don't move too much in relation to the Earth. That would have to be like a rocket going around the Earth constantly.
No, but the problem is that
Yeah,
everything
that's a
is
bit of a problem.
everything is already accounted for because of GR and SR. So there's no symmetry breaker. Everything they say, I also say about the current state of things. What we should do is ask. We could ask a satellite.
We need to make UFOs. To make
We
spacecraft.
need to ask the satellite, what are you seeing? How are you seeing Earth clock ticking?
Yeah, but having a satellite going really, really fast in relation to
It
the
doesn't.
Earth.
I don't think it has to
I
be
guess it
really.
could be done. It could be done. Like if it's a very small thing, it can be done. Sure. Yeah, it could be done. Yeah.
I mean, as far right.
I don't have the budget to do
I
it.
mean, the satellite. We never tell. Right, the satellite never reports back to us how it's seeing our clocks ticking. It's not like we're sending our clock ticking and the satellite is looking and saying, "Wow, you're ticking faster than you should." There's no there's no such experiment.
You'd have to like send a light ray and communicate, and then receive that light ray, and then you'd have to see like the difference between the clock of the satellite and that light ray.
Anyway, and
Yeah.
whenever I debate people that deny the ether, it's like it's never a discussion like this. It's never that they're trying to actually prove the like we're actually looking for
No,
symmetry.
people don't discuss like this. Forget about
When
it.
I talk, did you see when I talk to them how they attack me?
I mean, I turn off immediately because and just go watch something else because it's a waste of time. I don't even know why you subject yourself to.
Yeah, it's terrible. It's like nothing but personal
It's like
attacks. It's
it,
like
yeah, it's that it like they're not even like even well, there was one guy that was kind of interesting that I caught, which was like I don't know, it was like name starting with a T. There was some kind of sweet.
let me see.
Uh,
I'll tell you the name.
I don't know.
There was a guy
It's like
that
wearing a red shirt. I think.
yeah, he was good. Yeah, he was good. He's a
Yeah,
physics
it was
professor.
fine, but it was really like it just kind of hit a wall at some point
Yeah, Tappy.
that
His
he
name
couldn't
is
like process it.
yeah. His
But he
name
was trying to engage with it
yes,
properly. Yeah, but that was
definitely.
the only one I've seen
Yes,
from that conversation.
his name is Tapioca Weasel.
Yeah, that's okay. Yes, that's it.
Yeah,
That's it.
he was normal, and even but he took a
Yeah,
while to understand the rubber ducky. I mean, it took me a long
yeah. It took a bit. It took him a bit. He kept like saying different frames of reference, different
right.
frames of reference.
Yeah,
No,
yeah,
you're using a preferred frame of reference. Like, don't think about that. But that's a normal. That's normal. That's normal. That's
yeah.
someone that
He was very nice. He was nice, and he was
yeah,
engaging, and he didn't attack, and he was very nice.
yeah,
Everything, but he had to go. But he couldn't come up
yeah.
with,
I remember.
and I don't think he
Yeah,
understood.
you should talk to him maybe some other time to see if he processed it or not.
Let me.
Anyways, I gotta make a call and
Okay, I'll talk to
uh,
him.
we gotta call later or tomorrow.
Yeah, I'm
All right.
available
I think
whenever you
we've
want.
resolved this quite well,
Y-
at
y-
least in theory.
yeah.
Yeah. All
Okay,
right.
I'll
See
talk.
you.
Yeah, see
Always
you.
nice talking to
Yeah,
you.
thank you. Bye.
What? How do I leave this?
You click. You
Right.
click it. Bye.
My phone doesn't let me go back on anything. Oh dear
You
lord.
you should be able
Right.
to
Let
click
me let
it.
me just do this. Okay. I'll try something. I'll try to change the tab. All right. Yeah. Still simple. I like. Oh, I found them. I can go back now. Yeah.
Okay. See you later.
Yeah.
All right.
Right.
Okay. So he says. So I'm not really up for. Okay.
I'm like. Wait a minute. I'm like trying when I go to when I go to the chat to leave, I get on the whiteboard and then I can't leave the whiteboard.
You need to leave the
Okay.
white, and then you need to leave the thing. Did you? Yes, he left. Okay, we're fine. Okay. Wow, today's very productive. This is very exciting. This is fairly exciting. It would be interesting to go through ChatGPT and show. Wait, what do you mean three? Oh, yeah, we've been through everything. We went through everything. So it would be interesting to go through each one and prove that my ether model predicts the same, gives the same predictions. It would be interesting. I am curious about Mercury's perihelion, whatever that means. But I gotta go to the bathroom. Give me a minute. Bathroom break. Um. Oh my God! Somebody's cooking. I need to close the windows. Okay, let me just make a note that we are on a bathroom. How would I tell you that bathroom break? There's no way to tell you. Oh, here. Yeah, okay. So let me just say bathroom break. Wait, you can't see it. break, bathroom break. Okay. Give me a minute. All right, we're back. We're back, baby. All right. Okay. What do we got? What do we got? What do we got? What do we got? Okay, let me think. So I wanted to look into the perihelion or write a paper about like different things. Like how can we explain it? I mean, just go through. Where is this guy? Just go through all the proofs. Okay, you think this proves SR? Okay, it doesn't. You think Michelson-Morley experiment explains SR? Let me show you how it doesn't. Let me show you how this is so ridiculous. This is the experiment that Lorentz explained. This is like a non sequitur. Right? Is the word not, am I using non sequitur correctly? What's the definition? Non sequitur, something like that. Non sequitur. Any abrupt and inexplicable transition or occurrence? No. Logical fallacy. Any invalid argument in which the conclusion cannot be logically deduced from the premise. A logical fallacy. Wait. So it just means doesn't follow. So non sequitur is incorrect. So I would say just not evidence or so non sequitur. What does it mean, non sequitur? Well, what do the words mean? Oh, come on. Not to be confused with non sequitur. Okay. Formal fallacy. A non sequitur is a conversational literary device. Comedic. No, we need a formal fallacy. In logic and philosophy, a formal fallacy. Oh, that's a formal fallacy. A non literary device. What are you talking about? Conversational literary device. So there's no entry in Wikipedia for non sequitur. Where's the other non sequiturs? This use of the term is distinct from the non sequitur in logic. There is no. Okay. Formal fallacy. So non sequitur is just logical fallacy redirects here for an argument. I don't get it. This is not what I'm looking for. These aren't the droids we're looking for. Non sequitur does not follow. Is it conversational? It just says does not follow. It's like non sequitur is non sequence, I guess. Yeah, let's look at the etymology. Does not follow comes from the word non, not, and the verb sequi, meaning to follow. Yeah, it's like sequence. Okay, so it just does not follow. It's not. It isn't the droid that I'm looking for. So what am I looking for? So what am I looking for? Like something that disambiguates, something that separates, something that breaks the symmetry between the ether model and the non-ether model. Like they need to tell us. This is what I've been saying from the beginning. You need to tell me how to prove the ether. You can't just say the ether has been disproven. You have to tell me how to disprove the ether. Because the ether is a simpler model than GR. right? Because if I just add, if, because GR is just SR, right? It's all it is basically is SR with Newtonian gravity. There's nothing else really to it. It's not a theory of gravitation. It's just gravitation, Newtonian gravitation with SR. Okay, that's all it is. So it's not, there's no model, there's no modeling behind it. I have a model. I can and my model of the ether is exactly the same, but it's physical. It gives you SR. It gives you SR. Here is how it gives you SR. Oh my God. This is how it gives us SR. And it's right in front of our eyes. This is how it gives us SR, right? This is SR. So ether immediately gives us SR. And it also immediately gives us gravitation. So it gives us SR gravitation. But it's a physical model that gives us Newtonian and SR. That is what the ether is. I'm not showing you. Shoot, I hate it when this happens. This is SR. This is the mechanical SR, and this is also the mechanical gravitation. So it's already, everything is already done. This is GR. Done. It's a mechanical GR. I need to study GR. What is in GR that the ether doesn't give us? This is so strange. Let's see the story with the perihelion from Dr. Becky.
We were blocking out the light of the sun. We could see the stars behind it, and we could see that the light from them has been.
Yeah, the ether gives you this without this nonsensical curvature of space-time. So the sun, the earth. I don't know why the earth is twice. I don't get it. 6 months. Why do you care? I don't know. So we're standing on the earth. We're looking up and we see a star. But we know that the actual position of the star is here. Because when we were here, we saw it. I mean, you could have seen it most of the year. You could have seen it. This is just during maybe a month or two that you can't see it because the sun is hiding it. But fine, it doesn't. I mean, she should have shown it here. Well, it doesn't have to be 6 months earlier. We know the star is here. But during right, when you're looking here, you can't see anything until the moon got in the way. When the moon got in the way and was hiding the sun, now you could see and see the star. But we know it's not there. We know it's actually here. I don't know why she put it here. I don't get it. Oh, I get it. Okay. So it became bigger. It was magnified. Anyway, so we saw it during the solar eclipse. We saw this star, but you shouldn't be able to see it because it's here. It should be hidden behind. She should have shown that it's hidden. She didn't show that it's hidden behind the sun. So how could we see it? The only explanation is that the light is bending, which is completely predictable directly from the ether model, from Newton, from Galileo. It's nothing to do with a combination of SR with Newtonian, which is what GR is. So they're using GR, they're using a big, powerful tool for the wrong job. This is not what you use GR for. This is explainable from 10 different ways. I mean, at least 3 different ways. So I don't see this is not a disambiguation.
Been bent around the sun on their way to Earth. Now, we had to wait about 4 years to actually get that proof from Eddington in the 1919 solar eclipse. So we couldn't use that at the time in 1916 to prove it. The second test that he came up with was this idea of gravitational redshift. So a redshift is when light has its wavelengths stretched out to longer wavelengths or lower energies or redder colors. So we call it a redshift.
Again, completely I mean, if we're talking about the redshift due to Hubble, if this is the Hubble redshift, then of course it's explainable directly from the ether, and I don't see how GR explains it. Oh, because GR has a fabric that is stretching. Okay, which is nonsensical.
And that happens because of the expansion of the universe as well, mainly, is when we observe it.
Okay, so if that's it, then the ether model is mechanical, and I don't know like what mechanics you're using for the same effect. So as far as I know, the quantum mechanical, this is based on quantum mechanics. So the quantum mechanics needs a quantum field, and the quantum field they say is not mechanical. There's no ether. They have a quantum foam, but they say it's virtual. So I don't know what their model is. It's not clear. My model, the ether model, is very clear. I mean, especially when it comes to quantum mechanics.
But it can happen if light is also being dragged backwards by the gravitational pull of something as it tries to travel up and out of that curved space-time. Unfortunately, in 1916, Einstein didn't have.
And again, completely explainable by Newtonian or Galilean or the ether model.
Any way of proving whether that was right either. In fact, we had to wait until 1954 when a chap called Popper finally proved that it was happening around stars. And the third test that Einstein.
Completely explainable by the ether or Newtonian or Galilean. I should just name it. Ether is A, Newtonian is N, Galilean is G. So it's A and G. Completely explainable by A and G.
Came up with was whether it could predict planetary orbits. So, having observed a planet in a specific position one night, could you predict where it was going to be in a month's time from the equations that he derived? And in particular, he wanted to try and explain the orbit of Mercury because it had long been known that Mercury's orbit was a little bit dodgy. So, Newton's equations of gravity that had been sort of the leading theory of gravity since 1713 when he published Principia, and he took Kepler's laws of planetary motion and how the planets were around the sun and generalized it into this big theory of gravity. And so, whilst those equations gave really good predictions for where the rest of the planets in the sky would be after observing them, for a month later, for Mercury, it always gave slightly the wrong answer. And no one knew why that was for a very long time until 1859, when the Verrier published a huge long list of the positions of Mercury over a number of years and found that what was actually happening was that its perihelion was precessing. Planets don't actually orbit in perfect circles, they're actually ellipses. And so at some points it's further away, and some points.
1 second. Okay. Let's continue.
It's closer, and the point at which it's closest.
Let me drink some water. So perihelion and aphelion. So peri means near, helion means sun. I'm becoming hungry. Apo means far, helion means sun. Okay, so perihelion and apohelion. Okay. So perihelion close to the sun, aphelion far from the sun. Okay.
Is its perihelion, comes from the Latin peri meaning close and helion meaning sun. And what the Verrier found was that that wasn't always in the exact same place in Mercury's orbit. It was actually moving with Mercury. If you were actually to plot Mercury's orbit out, what it will look like is kind of like a spirograph pattern. Do people remember that game? I absolutely loved that game as a kid. You found me going all the time with like lots of different colored pens. Anyway, that is what Mercury's orbit would look like if you saw it over centuries. Now that diagram I just showed is a huge exaggeration of what this effect actually looks like. A single orbit of Mercury only takes something like 88 Earth days. And so you can't see it over a single orbit. You have to wait many, many orbits for this effect to sort of stack up for you to be able to see it. In fact, when the Verrier actually measured how much it precessed each year in the sky, he found that it was something like 1.5 degrees per century. A century. Or if you want to use a different unit, it's 5,600 arc seconds per century. So an arc minute is when you take a degree and split it into 60, and then if you take an arc minute and split it into 60 again, you get an arc second, which is a tiny, tiny unit. But sometimes movements on the star.
Okay, movement of stars around the central black hole of the Milky Way 0.1 arc seconds scale. What does that mean? That's like the size of this. This is the size of this arrow. It's 0.1 arc second. I guess it's like out of 360 degrees. So a degree is like 360 seconds, and an arc second is 360 arc seconds is 1 second. How does it work? And this is 0.1 arc second.
Are that tiny, and we do need to measure things.
Let me see
Or if you want
what
to use
she
a different unit,
says.
it's 5,600 arc. Orbit of Mercury only takes something like 88 Earth days. And so you can't see it over a single orbit. You have to wait many, many orbits for this effect to sort of stack up for you to be able to see it. In fact, when the
Leverrier observed Mercury for 41 years to spot it.
Leverrier actually measured how much it precessed each year in the sky, he found that it was something like 1.5 degrees per century. A century. Or if you want to use a different unit, it's 5,600 arc seconds a century. So an arc minute is when you take a degree and split it into 60, and then if you take an arc minute
Okay, arc is 60.
and split it into 60 again, you get an arc second.
Minute is 60. So this is 1 over 60 of 1 over 60, meaning 1 over 3600 of a degree. So it's 0.1. It's a tenth of 1 over. So it's 1 over 360,000 of a degree. And that is what we're seeing. This is this arrow. Okay.
Second, which is a tiny, tiny unit, but sometimes movements on the sky are that tiny.
0.1 arc second scale. Okay.
And we do need to measure things in arc seconds. Now, this wasn't that much of a surprise that this was actually happening, because in Newtonian gravity, it was expected when there's something that is quite close to a massive object, but is also being perturbed slightly by all the other objects in the system. So the main reason why Mercury's orbit does this is because it's not just interacting with the sun, but it's also feeling the pull of all the other 7 planets that are also orbiting the sun at the same time. The thing is, if you use the equations in Newton's theory of gravity to predict how much Mercury's orbit should precess per century, you only get something like 5,557 arc seconds per century, not 5,600 arc seconds per century. So there's 43 arc seconds of precession that's unaccounted for by Newton's laws of gravity.
No way. How do they do this calculation? I mean, it's such a nightmare.
Now, 1959, when Leverrier announced this, he said that 43 arc seconds unaccounted for could be due to the fact that the sun isn't perfectly round. It could be an oblate spheroid, which means it's kind of squashed at the poles, just like what Saturn is, because it's rotating very quickly. And it did turn out that that plays a small part, but it's not enough to account for 43 arc
Everything's like, how I gotta see these calculations.
per century. Or Leverrier said there must be another planet inside the orbit of Mercury orbiting the sun that could explain the fact that we're getting this extra 43 arc seconds. And if we put that into the equations, it should all come out with 5,600 arc seconds per century. Now, at the time in 1859, that was the most favored hypothesis, because 13 years earlier, in 1846, Leverrier himself and Johann Galle had actually found Neptune. They discovered Neptune through a motivated search for another planet because of the weird orbit of Uranus that couldn't be explained, and was suggested the only reason that it was like that was because there was another planet beyond it that was perturbing it slightly and pulling on it more. So as odd as an extra planet inside the orbit of Mercury to you and me sounds, back then it wasn't such an outlandish idea, because, well, they only just discovered Neptune. It was that feeling that there could be something else out there that had never been spotted. And so this hypothetical planet inside of Mercury was dubbed Vulcan, after the Roman god of volcanoes.
Okay, so they thought there was another. Wait, somebody on Discord is talking to me. Hey. Maybe she wants to join me. Join me. T. Let's continue. This is very interesting. So here's Vulcan inside of Mercury's orbit. Okay.
And fire and forges. Now, for the rest of the 19th century, confirming that this hypothetical planet Vulcan existed was people's top priority. And obviously, people wanted to be the person who discovered it. And there was a lot of false claims throughout most of the 19th century, including people that were adamant that they'd seen something transiting across the face of the sun, despite the fact that someone who was observing the other side of the world at the exact same time didn't see anything. There were people that claimed they'd spotted a planet during the solar eclipse, very close to the sun, in a position where no known star was thought to be. What really highlighted the fact that these were all false claims, though, was that every single observation gave us a different answer for the properties of Vulcan and Vulcan's orbit. So some would claim that it was further in towards the sun, some claimed that it was further out, some more massive and some less massive. If they'd all agreed, then that would probably have been quite a convincing hypothesis. But it became pretty clear pretty quickly that this hypothetical planet wasn't actually there and couldn't explain the strange precession of Mercury's perihelion as it orbited the sun. Now, this is where Einstein comes in 1915, with his theory of general relativity that said that masses curve spacetime and all other objects travel along that curved spacetime. And the equations that he came up with essentially describe that curved surface, or geodesics as he referred to them as, that all the masses would then be traveling along. And so from that general equation of curved surfaces, he managed to apply it to the solar system and get out equations for what the orbits of the planets would be like, given the fact that they were traveling on the curved spacetime created by the sun. And he found that his general equation for the planets reduced down to exactly Newton's equations, just plus one extra term. And that extra term was 2gm over c squared r cubed. So g is the big gravitational constant that tells us sort of how strong.
But what is the mechanical explanation for this term? Wait, let me share. Let me share my stream. Did I share my stream? I think I did. In the Discord. Yeah, it's already there. Okay, special relativity. Okay.
Strong gravity.
So gravitational constant is very tiny. That's good that she put it like that instead of like 10 to the negative whatever. This is very nice. Meter cubed per kilogram cube per second squared. Yeah, it's really tiny. Divided by c squared, really tiny. Divided by r cubed. Yeah. So for the faraway star planets, this destroys the effect.
He generally is in the universe. M is
2gm over c squared is the escape velocity from any mass. No? Maybe the square root? It's interesting. This 2gm keeps coming up. This is the mass of the object curving space, the sun. Okay, this is the sun. Anybody on? Mhm. Okay, let's continue.
is the mass of the sun, c being the speed of light, and r being the distance of the planet, i.e. Mercury in this case, from the sun. So it wasn't that Newton's equations were wrong at all. It was just that that term disappears when you have either very small masses, so like the things that we experience on Earth when we throw balls in the air or projectiles, or very large distances between objects, like with the majority of the planets in the solar system. It's just that for Mercury, which is much closer to the sun and so has a much smaller value of r, i.e. distance from the sun, that term
So this, but what's mechanically causing it? This is time dilation, right? Because this is SR. All the GR is Newton plus SR. There's nothing else. Why would you get this because of SR? How does SR do that? Right, basically, right, if we look at all we're going to say is that Mercury's clock is slowing down as it's closer and closer to the sun. Mercury's clock is slowing down, but that shouldn't impact Mercury's path. Why should the path be changed? I don't know. I don't know.
term no longer tends to zero. If you divide by a small number, you get a much larger number. And so that term is much more important for Mercury's orbit than it is for any other planet in the
I mean, it's okay that it's math, but what's the mechanics? What's the interpretation? That there's like an extra curvature? Well, why? What's causing this extra curvature? What could be causing it? Like if I'm looking at the ether model and that the ether is flowing into the sun, what? It's like the as you get closer to the sun, the ether something grows. The ether's effect grows beyond just the Newtonian effect. Why? All I get is time dilation I mean, what else could it be? I mean, Mercury, what? The mass of the sun increases. Mercury perceives the mass of the sun to be bigger for some reason. I mean, Mercury is looking at the sun, it's observing the sun, it's moving relative to the sun. As it's moving relative to the sun is looking at Mercury. The sun perceives Mercury to be what? It's moving through the ether, so what? It's making it more massive, so Mercury becomes more massive, so what? It's still tiny. But it could be that the rest of the system corrects for Mercury's mass. Is it corrected? Is it a correction of Mercury? I mean, how does it work out? I'm trying to think. How would this work? What is that term? What is that term? But the mass of Mercury doesn't even show up in that equation, so that's not it.
The solar system. So what Newton's laws really were an approximation that just didn't happen to hold for Mercury. It's also worth noting here that Johannes Kepler, who came up with the laws of planetary motion that Newton took to apply to his theory of gravity in Principia, they were written down in the early 1600s. And that was back in a time when people, including Kepler, thought that the speed of light was infinite. Now, in Einstein's extra term, you divide by the speed of light squared. So you're dividing by infinity squared, which is infinity, and if you divide by infinity, then you're going to get essentially zero. Mathematicians will likely say that dividing by infinity gives you zero. It tends to zero, is what you should technically say. It's a singularity.
No, dividing by infinity doesn't tend to. It's just dividing by infinity. Well, which infinity? Positive, right? They would say, is it positive or negative infinity? If it's positive infinity, well, they would say there is no infinity, right? But physicists would say the same. There is no infinity. You can only tend to. So, all right.
But I'm happy with just saying that it divides by zero.
It's just a convention.
Sorry, I feel like all of the number file professors are going to descend on me for saying that. But essentially, it gives you something incredibly, incredibly small. And so that extra term of Einstein's would always have disappeared back in the 1600s when they thought that the speed of light was infinite. But we now know through many, many different painstaking ways of measuring it that the speed of light is not infinite. It actually has a finite speed of about 300 million meters per second, which is something you can measure in a microwave with some marshmallows, which is a super fun experiment for a Sunday afternoon and would.
Yeah, you can measure the speed of light in a microwave with cheese. Hello. I'm watching a video. What am I done with what? With watching the video? What?
Physics.
I can take a break. I mean, I was gonna take a break either way. I mean, I'm watching anyway. What's up? How are you?
That was just so boring.
What, you were watching the stream?
No, I had to leave.
So what was boring? Well,
All of it. That's why I left.
I know, but that was like a million hours ago. What's up? What's up? Yeah.
I died because I was bored.
I know. I know. Look, I understand. Like, I would have been bored too. I mean, there's a limit, I can understand. It's not like I can't understand. I mean, like, if you talk to me about most things, I would kill myself because it's so boring. So it's not like you're the only person who gets bored by things. I get bored by things that are disinteresting. So it's fine. It's fine. Everything is fine. Everything is fine. Everything is fine. Everything is fine. It's all fine. It's all fine. So I see that remember choking hazard?
Yeah.
So she came to visit, but she never I sent her an invite. Let me. You want to You want to go to politics and debate people?
Yeah, do you want me to make a room for you again?
Whatever you want. It's up to you. If you want to make me a room.
Alright, I'll do that.
Okay. La la la. Okay, while you're making the room, I'll finish watching the video.
Would highly recommend it. You won't get the most precise answer, but you'll get something in the right ballpark, which is pretty damn cool for a microwave and some marshmallows. So what Einstein did next with his extra term.
You're doing it? Yeah. Okay, I'm waiting. So, where? Where is it? Mr. Slave asked me anything? Elo! 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 What?
Said hey.
Hey.
Would work out how much of an effect it would have on the predicted position of a planet, and in particular, how much extra precession of the perihelion of Mercury did it give you? And when he plugged in the numbers, he found it gave you an extra 43 arc seconds per century on that precession. The estimate at the time of the amount of precession that was unaccounted for was 45 plus or minus 5 arc seconds per century. And so Einstein, rather anticlimactically, at the end of his paper, sort of announcing general relativity and giving this proof of it through Mercury's orbit, stated that it showed full compatibility, i.e., it proved his completely groundbreaking theory. It's worth stating here actually that to do this, Einstein actually made a massive approximation when he went from his big general theory of geodesics and curved spacetime to giving the equations for the planets around the sun. It actually took Schwarzschild a couple of months later, having looked at Einstein's work and going, yes, this is great, to actually come up with the non-approximated solution to all of these equations. But with the advancement of telescopes and radar throughout the 20th century, we've actually been able to confirm that the same thing happens for the other planets. All the other planets' perihelion processes as well, just by a tiny, tiny amount that is also predicted by general relativity. So for Earth, our perihelion processes 3.84 arc seconds per century because of this effect. Venus, 8.62 arc seconds per century. It's so small that back then people would never have actually been.
Anyway, so now we wait. We wait for our victims.
Able to observe it and realize that there was actually a problem. I mean, this is really cool, but I bet a lot of you are thinking, why should we care? Like, yeah, we have a better theory of gravity now, and we can explain how the orbits of the planets move, but that doesn't really change things down here on Earth, and we're working with the small masses that Newton's equations just give a good enough approximation to. It's why we still all learn them in school. Well, it's actually our understanding of general relativity that allows us to actually have a global positioning service. So the satellites that go around the Earth, that essentially every time you want to know your position on your phone from maps or weather or whatever it is, they send a ping to the satellite, and they triangulate between 2 or 3 different satellites where you are on Earth down to, meters precision. And that's only possible through our knowledge of general relativity, because the satellites, as they're moving around the Earth, they're moving in the curved space-time that the presence of Earth gives us. And so they're actually affected by this idea of gravitational redshift. All of those pings of communications they send down to Earth and back up to the satellites are affected by this gravitational redshift. And
Anyway, learn about echinoderms. No ESL. Oh, atheist debate. Chess, let's play.
And so if we don't correct for the fact that the timing between them will be slightly off each time, they would be out by something like 10 kilometers per day. So the next time you pull out your phone to use maps, or to look at the weather for your exact location and get minute by minute when it's going to rain and when it's going to stop raining, or you use the sat nav in your car, just think of Mercury and of Einstein and of Schwarzschild, and just say a little thank you in general to physics. And that's only possible because we found it. And
Okay, I don't know. I'm becoming a hungry personnel. Do you know how to say person in Portuguese?
Persony.
No, it's actually you spell it personal and you actually pronounce it pessoal. Pessoal.
That's so weird. That one's weird.
So usually when you say hi to someone, you say like in a YouTube video when you say hello everyone, you usually say hola pessoal. Hello super. Oh my god. Wait.
What does Mr. Slave mean? What is this all about?
I am Mr. Slave. It's nothing. I'm just a philosopher. I just
Are you a
debate.
slave to something or?
Yeah, I'm a slave, but that's
Pretty
irrelevant.
renowned physicist at this point.
I'm a renowned
Alternative physicist.
a renowned alternative physicist, pretty much. Do you know physics?
I know like the Earth goes around the sun and the moon goes around the Earth.
Well, those are certain approximations. I mean, you could say anything you want. I mean, but yeah, it is a
I know things that have mass have gravitational pull, man. I know that. You know, they stretch space. They stretch space and time.
That's Einstein's GR. Yeah, I disagree.
You disagree? Oh wow.
Yeah, I disagree. A lot of people.
What do
Well, I certainly disagree. Yeah, I'm researching it right now.
You're
Wait,
researching it
Mr.
right now.
Slave?
Hello.
Wait, why is your name Mr. Slave?
Oh, it's for historical reasons. I'm historically a slave. I'm a historic slave.
What do you mean?
Are you African American?
No.
Yeah, that's what you made it sound like.
I see. No, I'm an
Are you
actual.
European?
Are we live on Twitch right now?
We're live
Oh my
on
god.
the YouTube. We're live on YouTube.
On the YouTubes, on
Um,
news of the
Are you
tubes.
European?
He sounds European.
I am European skinned.
Skinned. What does that mean?
My
Okay, so
skin
you're one of those
is
Someone
slightly
skinned
white as
my
possible.
homie, dude.
someone's what?
You were skinned, dude.
These viewer skinned?
Never mind. You're
What
killing
does
it.
European skinned mean, dude?
Oh, I have European
He's trying his
skin.
hardest to be white.
I have European.
But like, what is European skin? What is like?
My skin is
What counts as
European.
European skin?
My skin has is.
Are we talking like texture, like color, like what do you mean, like skin?
I'm a
There's lots
whitey.
of attributes. of
I'm a
skin.
whitey.
I mean, there's plenty of Europeans that their skin isn't pale, you know.
Yeah, I'm like I am fluorescent.
You're fluorescent.
Yeah.
So now you're neon.
Yeah, I'm neon.
Be over here electrifying nitrogen and shit, bro. That's crazy.
I don't know what that is. Anyway, does anybody want to debate me on any topic? I usually
You're a physicist, but you don't know how neon lights are created.
Do you know how neon lights are created?
I just explained, bro.
You just explained how neon lights are created?
Yeah, they put gas in tubes that are vacuums, and they electrify them, and it glows certain colors based on the gas.
Oh,
Crazy.
so you know physics.
Oh wow, that's physics. I thought it was just light. Is light physics?
Of course. What do you think is
Everything's physics.
Can you explain to me how a neon glows, like a neon bulb? How does it glow?
I think it emits certain wavelengths, you know, radio waves and stuff like that, Brody.
Can you explain it at the quantum
Light
mechanical level?
waves. Yeah, bro, things be like jiggling around and shit, and then it hits your eyeballs.
Yeah, what do you mean things? What is jiggling? And how does it arrive?
I think photons. I think the photons be jiggling and shit.
What's
You know, they be making waves.
What's a photon?
A photon? It's a little particle that like hits the back of your eyeball, and your eyeball goes woo.
Wait, so it's
all the little cones and receptors.
So it's a particle?
I don't know. Maybe. I mean, I'm not the physicist here.
What if it was just your fat ass?
These are just like a layman's definition of things, because you know I don't have a degree in anything. I'm not a studier. You know, I don't study things. I just do.
Yeah, but like you wouldn't be the first person to say that it's a particle. Right? If you ask
Oh, I wouldn't know. I didn't invent the word particle, Brady.
Right, but if you ask like if you watch a YouTube video from like one of the science explainers, whatever, communicators, they would say that it's also like it's a particle and a wave or something, right?
Oh yeah, I believe it's yeah, something like that, bro.
Does that make sense to you?
I don't know. I'm not a physicist. I don't study this stuff.
But you've heard physicists say that light is both a particle and a wave.
I don't know if my high school science teacher was a physicist. I don't believe so, no.
But you've heard people, experts say that light is both a particle and a wave, right? You heard it. I'm not the first person to tell you.
Yeah, if a high school science teacher is an expert, sure, yeah.
But
that's what.
But you've heard
I don't have higher education, right? I don't talk to these professors and shit, bro.
No, but I don't either, but like if you watch YouTube videos about science, all the science communicators, they tell you
But
like,
I don't watch YouTube videos about science, dude. I don't know.
so you only learned this from your teacher in high school?
Yeah, bro.
You've never heard anyone else say light is both a particle and a wave?
No, who the fuck talks about light in like everyday, day-to-day like topics unless you're like in school?
So you
I don't talk
remember,
about light. I just see it.
so what you're saying that light is both a particle and a wave is what you remember from high school?
Yeah.
Hmm.
Mm-hmm.
So your teacher said that light is both a particle and a wave?
Something like that. I believe so.
So does that make sense to you?
It made sense to me at the time, yeah.
Does it make sense to you now?
Yeah, I believe so, yeah.
What do you mean? Does it make sense that something is both a particle?
Yeah. A little homie be a particle, but he be waving around, you know what I mean?
No, I don't know what you mean. How can you be
You,
both?
well, you know,
Hmm?
there's plenty of people that are like both things, you know. It's
What are we doing
there's
now?
people that are black and white out there, you know. They're called
This
mixed.
argument is already old and going in
I didn't know it was an
circles.
argument, dude. I'm just saying. That's what I've heard. These are things I've heard.
I'm saying, does it make sense to you that something can be both a particle and a wave?
And I'm telling you, yes, dude, it makes sense to me.
So can
I don't see
you,
why it couldn't.
right, but like a wave, when I think of a wave, I think like of a wave of water, for example, right?
Yeah, and a wave of water is made out of like atoms and shit, bro.
Yeah. I mean, it
It's
goes,
both at the same time.
right, but it goes through, it's like a propagation of something through molecules and atoms, or yeah, molecules of water. It goes through the molecules of the water.
You know, atoms are mostly like empty space, you know, that's what they say.
Yeah,
And like my hand don't be phasing through walls and shit.
yeah, that
You
makes
know?
sense. I don't
I
have
think they can be both at the same time.
how. Like how can something be both a particle and a wave? Sounds like a nonsensical statement.
Just like how I'm brown and white at the same time, you know?
Well,
I'm white. I'm
whatever.
white and brown.
Yeah,
You know, my dad's brown. No, my dad's white, my mom's brown, you know, I'm both.
yeah,
Come on.
that's not confusing. But a particle and a wave, that's confusing.
I mean, why can it not work? I mean, you're the physicist
I'm
over here
trying to
explain
imagine,
why it
because
can't be.
that's exactly my point. Like I think when everybody
Why
says
can't
that,
it be?
I can't imagine it. I don't know what it would be because I can't imagine it. To me, it sounds like a lie. If I cannot imagine it,
You
then
don't think a bunch of little things can like organize into a wave, right? That's just impossible.
I mean, I cannot, like a water wave is not a particle. Like a baseball is a particle. Like water is composed of little particles.
I don't understand you, dude.
Like I don't like it's either a wave or a particle. It's either a baseball moving through something or it's a wave that is waving.
Why can't that baseball move at a frequency like a curveball? Hmm?
A baseball can vibrate. I don't have a problem with that, but it
And
moves.
that's what waves are they not? They move. Waves are a frequency.
Waves have a frequency, but
Exactly.
no, completely
Mhm.
different. No.
Waves move at a frequency. What makes a wave then?
Look, a
Hmm?
wave, like a wave, like a water wave, is the propagation, I would say, of energy, of an amplitude through the water, through the water.
Moving at a frequency, like
Yes,
moving up and down, bro. Yeah. Hmm.
yes,
A
but
baseball can do the same, bro.
yeah,
It's called a curveball. You can go circle, 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 spinning in a circle. You know.
yeah, yeah, but yeah, he left. Yeah, yeah. Mm. Let me see. see the other server. There's no one on any server. So right now, Mercury's orbit, I don't understand. I cannot explain Mercury's precession. So that's a problem. What?
Capybaras.
Who's DDDN? Quantum physics is whack. They didn't say it is a particle and a wave. No, no, no. Who is this? Is this the guy that was here? Is that the same guy?
Sick comment, honestly.
It's a big difference. If I cannot imagine it, what dude? Finish that sentence. He's texting, but he's not joining us. Why don't you join us, man? So how is he? Oh, he's watching us probably on YouTube. Okay, got it. End it all, you nasty, says Kaidism. All right. When was this? This was like 10 minutes ago. All right. Anyway, he says they say it behaves like both particle and a wave in certain experiments. Yeah, but I'd like to be able to imagine what it is like. What is a photon like? Like I'd like to get a straight answer. What is a photon? Like just telling me things that I cannot imagine, that's not helpful. Like sounds like a lie. Boo-hoo, you can't imagine something. Yeah. If I can't imagine it, I'd like to be able to imagine it. Like like what's the point of you explaining something if I can't understand it? I bet it is a long list of shite you can't imagine. Okay, and there we go. Like it immediately going to personal attacks. Okay. Have a great rest of your life, dude. It's whatever. Let's get back to Dr. Beki. Dr. So, how can I explain Mercury's perihelion using ether? Mercury perihelion precession with ether. How would that work? Etheric
The
explanation.
precession of Mercury's perihelion could potentially result from etheric friction and the buoyant force of the ether. As Mercury travels through the dense ether enveloping the Sun, it experiences friction due to the ultrafine particles of the ether.
No, there's no such interaction. I don't believe there is such interaction with the ether. I doubt it. It's on the stream. I'll give you a link to my stream. La la la. Oh, okay. So somebody's explaining that Mercury is interacting with the ether, and that's why its orbit is like a little bit unpredictable.
This frictional force could slightly
He says there's a frictional force, which I don't think there's such a thing.
alter the velocity and direction of.
If there was a frictional force, then we would see all celestial mechanics suffering from this friction.
Mercury's motion over time, leading to a gradual shift or precession in the perihelion of its orbit. Given that the density of the ether is highest near the Sun and decreases with.
No, it's actually lowest near the Sun. The pressure near the Sun is lower because the velocity of the ether is faster near the Sun. So the pressure is lower, and the pressure gets lower and lower. You have actually a pressure gradient that causes the flow of ether from high pressure to low pressure. The pressure has to keep getting lower and lower in order for a gradient to be. Let's say there's a constant gradient, so that's how you get acceleration.
With distance, Mercury could experience a buoyant force as it orbits. This
A buoyant force, I don't see it.
force
We would have seen there's a buoyant force there. I don't see it. I just don't see it. You could say that. Let me see. I have a message. One second. I have a message. La la la. What happened? What happened? What happened? Mr. DDD, and you're the only person watching my stream, but you're not having a nice conversation. So I'm going to ignore your comments when you're not being nice. You know that. I have another comment. F, you are bad at this. Bad at what? At doing research? Okay, you know, you can, if you can do better, you're welcome. You know, try and do better. Do better. Okay, back to this. So, but these are very nice ideas. Certainly nice ideas. Well deserving of my subscription.
similar to what a submerged object experiences.
I don't see how you get buoyancy. That doesn't make any sense. One second. More message. Oh, I have a visitor. A friend. Yeah, a real IRL. So I have to tell her what's in the menu. She's coming over to eat. Uh, hmm. So I think I have all the food that she needs. Okay. I think I have to go prepare the food because she'll be here very, very shortly. La la. I can't hear you. What? No, I'm not going yet. I just asked her when she's arriving. But I really should start making the food. Let's see. Let's finish
In a
this.
fluid might act as a resistance against the gravitational pull of the sun.
No.
This could subtly alter the orbit of Mercury, thereby contributing to the observed precession. The precession of Mercury.
No.
The precession of Mercury's perihelion refers to a gradual rotation or advance in the orientation of the elliptical orbit of the planet Mercury around the Sun. In a two-body system,
Oh, one person watching. Who's watching? Who's watching? All right, let's continue.
such as a planet orbiting a star, classical Newtonian physics predicts a fixed and unchanging orientation of the orbit. However, the observed perihelion, the point in Mercury's orbit closest to the Sun of Mercury, advances slowly over time at a rate that couldn't be accounted for solely by gravitational influences from other planets. Einstein's general theory of relativity provided an explanation for this anomalous precession. According to the theory, gravity is not just a force between masses, as described by Newtonian physics, but rather the warping or curvature of spacetime caused by mass and energy.
But Einstein just took Newtonian gravity, added SR, special relativity. That's all it is. And I'm accounting, the ether accounts for Newtonian and SR. So where does this precession come from?
As a result, the orbit of a planet is influenced not only by the gravitational
Hey, what's up? That he's broke?
No, sect, like, religious group of people.
Okay.
Basically,
Mhm.
that experience was fun, but and fun and very unusual.
Hmm. Was he nice?
He was pleasant. He
Mhm.
wasn't offensive or mean or whatsoever. He was pleasant, but at the same time, I felt like there is something wrong with him because he was very, very emotional, like literally crying during the conversation, etc. And that's the second person representing that group because 2 days ago I spoke with another one of them. He
What's
was
what's the
literally doing the same thing.
what's the group?
So they do not have any kind of name. They so basically the main idea is that they are Christians,
Okay.
but they use a lot of words like views, perspective, first person view, consciousness. The main idea is that they want to describe consciousness by some sort of a view, idea, or whatsoever. It's hard to follow, but
Hold on. I gotta stop you. I have a guest coming over, so I gotta go later. Let me send. I'll send you a request to be a friend, and we can talk. I'll let you know when I'm back. Wait, friend request
no
failed.
worries. Take it.
It says failed.
Take your time, man.
Why can't I send you?
Oh yeah, wait a second. Let me change that because I yesterday did it and uh, how do I change this request?
I
You
sent
can
you hi.
DM me or
So
yeah,
so I'll let you
that's
know
enough.
when I'm back. We can continue the conversation. I gotta go make food, otherwise I'll die.
Sure.
It's
No worries, man.
it's really interesting. I'm really curious about what you're saying. It sounds really interesting. All right,
Sure.
I'm leaving. Thank
Yep.
you. Bye bye.
Bye. Bye.
All right, I gotta go make food. Thank you, Calrissian, and thank you, well, Augustine. Thank you for all your comments. Thank you, everyone, for joining us. We'll see you next time. Bye.